en un día.
Quizás. Y cada canción, sí.
Y la cena estuvo muy guay, ¿no?
¿Ah, sí?
Sí, muy, pero ¿cómo levantarnos?
Pero era los chistes de Fano.
No, pero que llegamos acá.
Bueno, pero era oculto.
Claro. Estábamos acostando a la 1, la 2 cansada.
No,
Pero levantar
yo fui a casa de por eso digo el año y como había tenido y quería pedir la...
está en mi
Sí, desde ayer me puse hasta la tienda que se ponía a un equipo. No la... Siempre lo había rechazado. Pero bueno, bien.
Pero ayer estuvo bien, pero claro, desde por la mañana aún, pero luego la clase.
Todo el día la misma.
Yo, sí, bueno,
Yo también estoy avanzando. Yo estoy caminando porque no gusta.
pues ahí lo que me pongo hasta
No puedes
mañana.
estar sensible que sabes.
Yo, como, ay, no me malo. No tengo ganas.
No me calientes.
Sí, es que no tengo ganas. No me marees hoy, no me marees. Y esta mañana me tomé un café y ya está. Por eso mismo.
Y no solo me hago, porque lo ayer también tomo café. Cuando me hago uno, se me nota. Me lo noto.
Sí.
Porque no estoy.
Sí, yo mira, de normal no tomo. Pero domingo que acaba de comer y dice, como no me tomo el café, voy a estar son 3 horas,
Sí,
eso no es normal. Pero bueno, bien, bien. Muy guay. Y la sala muy guay, ¿eh? Me gustó mucho.
Yo cuando te veía digo, es que ahora va a ser bajo, cuando salga yo, porque
No,
es súper
cada uno
activa.
tiene su estilo y yo mucho tiempo y soy muy Dani Rovira, o sea, esto
Claro,
salir a cada 2 por 3 ahí en plantón.
claro, pero como muy animado, todo yo. Claro, yo me lo había preparado en plan lecture. Lecture, digo, pero va a ser esto un bajón.
No,
Pero bueno,
pero
bien,
guay.
al final se les para. ¿Lleváis?
Pues sí, pues sí. Ay, y a ver, tenía que hacer a las 9:30 y le he dicho, pues mira, yo ya me voy a ir, la misma hora alguien,
Sí.
y ahora pondré a cargar.
Todo eso de la frontera que es la semana que viene, los martes miércoles, tenemos
El miércoles por ahí,
miércoles de la semana que viene.
20
Algo así.
que yo creo que ahí ya todo el mundo está en plan.
Quiero irme a la casa por Navidad.
Sí, no, pero en plan, no me voy a casa, no me pongan nada que me maree demasiado. Entonces, tú te lo dije a ti o a quien te lo dije, queremos hacer un febrero en 1 hora.
Ah, bueno.
O sea, la idea es,
Listo, así.
sí, que la gente se junte. Y bueno, y no sabemos cómo va a hablar cada uno, claro.
Ahí es una que hablar. Si hubiera tenido un poco más de tiempo para
Pero
preparar
nos
eso.
lo está diciendo mucha gente.
Porque eso
Que
está muy bien.
dice, el año
Yo tengo
que
un
viene,
tema que digo, el tiempo en matemáticas, en física, tiene además fronteras. Es en física, nos interesa en variedades con fronteras, que la bajo al título de la conferencia.
enganchabas ahí.
Y además es física, y es por la gravedad. Es el borde de Skype.
Pero mira, pues.
Pero es que no tengo tiempo porque
Juan Margalef hace
sí.
muchas cosas de antropología y de fronteras y tal.
Sí, sí, sí. Que a mí me gustaría, pero es que claro.
Pero no hay prisa, o sea, esto es como, mira, vamos a ir a Chernobyl y es que.
Si lo haces el otro año, yo me apunto y doy.
Y sí, yo creo que.
Sí, he retrasado mucho por la charla de ella y también por ciertas historias. Claro, tengo que. No puedo ya retrasar tanto.
Bueno, sí, a mí en el puente me decimos por todo menos una asignatura. Están los pobres, es que no voy a hacer la última, entonces bueno. Pero este fin de no me toca encerrarme otra vez, porque quería hacerlo bien. Bueno, bien. Y también pintamos. Ayer salió todo, creo que bastante bien. Pues vino bastante gente para lo que podía hacer sobre Valencia.
Sí, bueno, yo no lo sé. Como nada,
No, pero
yo sí que me pensaba.
y bastante gente joven.
Claro, yo sí que me pensaba. Sí, mucha gente joven, que era como más un escenario. Y al hacer así más improvisado.
Que la sala de Tramayera es más chiquitita. Pero a mí me gusta más.
Sí,
porque,
más acogedor, más familiar. Yo
por
no
ver a la
tenía
gente.
que me daba más.
Ya,
está como
sí, o sea, no, y está en el auditorio, como que estás ahí en mitad de la nada, pero como no veo realmente a la gente, ¿no?
Claro, yo pensaba que era algo así, que iba a mirar un foco,
Claro, que no es como...
que me ciega y no veo, yo a lo mejor veo sombras.
Manchas negras, dices, ¿me estarán haciendo caso? No lo sé. Estarán durmiendo,
Ah,
probablemente.
exactamente, algo. Yo pensaba que era ese rollo. Pero claro, a mí me trae, no, que me intimidaba un poco por eso
Pero
también,
bueno,
claro.
no había... O sea, no era tan grande que...
Era más familia.
Sí.
Entonces, esto no se lo
Y
decía.
Avelino, ¿sabes? Me dice, mira lo que me ha escrito Leonardo, que con este tío, que yo interacciono mucho en Twitter y no sabía que era él. Y yo que sé con
Dice,
quién.
Leonardo es el exfundador o algo así.
Sí, el primer
Sí,
presidente, Leonardo Fernández Jambrina, claro, yo lo conozco de época de empezar en la serie, pues ellos eran pues, Ruth, Alex, Leonardo, pues eso eran no los más mayores, pero eran un poco los que
y
estaban.
Leonardo, una vez tengo de seguridad en los nombres, es una
Sí.
matemática.
Bueno, él hizo matemática aplicada en
Por
la
eso,
Politécnica.
como había oído explicar, puede ser matemática aplicada por física, dependiendo del departamento.
Ahí está en mitad de camino un poco.
Claro.
Y bueno, y él, pero interacciona, claro, yo sí que lo conozco, ¿no? También dice, no lo conoces. Y en la charla me dice, ¿y quién es? Y digo, pues Leonardo Cambrina, me sonaba más un apellido porque era la Vicente. Digo, este es el primer presidente de la Segre, vale, pero se queda así y ya está. Luego le escribe, porque se tuvo que ir en el tren, por eso no hablé con él luego ya, porque a las 9 tenía el tren. Y entonces me dice, a ver, Isa, que con este tío yo interacciono en Twitter, que me ha dicho, Adelino, que no nos ha dado tiempo a saludarnos bien, que te he puesto cara. Y dice, porque no sabía quién era. Y yo, hombre, yo te he dicho quién es, pero yo no sé lo que tú haces por Twitter, yo te voy a saber. Y sí, sé que me dijo el nombre de Twitter y claro, no tenía nada que ver, era un Leonardo no sé qué.
Leonardo,
No, bueno, no era Da Vinci, pero era Leonardo, otra cosa.
cosa.
Bueno, no sé, otra cosa. Entonces digo, bueno, pues ya os conocéis, o sea, las caras, no había hablado mucho, pero no, se tuvo que ir y no hablaron mucho. Y le digo, pues mira, dice, es que para ti es normal, digo, hombre, para mí es normal, no, pero yo lo tengo en otro contexto, ¿no? Y estuvo guay y que Pepe nos presentara. Bueno, cuando...
Pepe no se lo esperaba, yo creo que tiene...
¿No? Cuando se lo dije a Gonzalo, pues estábamos a Gonzalo a ver cómo lo organizábamos, en plan, me gustaría incluir de alguna manera a Pepe como representante de los dos departamentos, ¿no?
Sí.
Y dice Gonzalo, pero ¿cómo lo hacemos? Porque si se ponen a hablar todos no vamos a terminar nunca.
Se enrolló un poco.
No, pero está bien, estuvo
y estaba nervioso y digo, quiero empezar ya.
Venga, Pepe, tira. Pues le digo a Gonzalo, hombre, Gonzalo, si los primero hablar a todos, primero, es que va a ser muy largo y segundo, que a lo mejor ellos tampoco. Entonces al final el acuerdo
cuando le dieron el micrófono,
saludar un poco y que eso, que te lo iba a presentar a mí y que Pepe te presentara. Y que fue como, mira, guay idea, porque sí, se le da visibilidad a la persona, pero tampoco es hablar ahí tipo, ¿no?
Sí, algo
y entonces
más.
yo creo que entonces fue como, bueno, ahora voy a hablar un poquito. Pero en plan, guay. Estaba súper feliz, a mí me lo digo, estoy muy feliz, ¿no?
Sí.
En su salsilla ahí, yo me gustó mucho. Bueno, voy a poner a cargar cosas. Bien.
Muy bien.
Me hubiera gustado ir, pero tenía cosas acumuladas y de hecho me acosté a la 1. Tenía las 12 y pico en mi casa. Un plátano y un yogur.
Solo bueno de venir.
Siempre es mejor el invitado que
Claro,
que el
mucho
host.
mejor. Estás aquí y tienes, aparte del trabajo extra, de estar de host, como dices, luego te vida. Me pasa lo contrario el viernes, porque el viernes va a Pepe a Madrid a dar una charla en los seminarios estos polivalentes y voy a conseguir a la India también. Es una cosa que tenemos fijado la fecha de julio. Yo tengo un día en casa de 200, entonces no me puedo quedar a pues, cada vez más salud tengo que ir corriendo a mi casa, ya no hay 38 horas. Eso no me pasa así.
Claro,
Invitar.
Visitante.
Tú acabas, sueltas tu rollo y ya.
Yo me lo pasé genial y te vi mi maravilla. pero llegué a mi casa y esa ya ha sido como, no quiero, o sea, quiero seguir durmiendo. Pero bueno, bien, y hoy lo mismo, que apareceré y apareceré. No me vaya pudiendo y no pudiendo. Y sí, me parece.
Aún no he empezado, no he empezado todavía. Llegamos a tiempo.
Falta la
Claro,
de...
mira, claro.
¿Tienes por ahí?
Es el mío.
Ah, vale. ¿Vas a conectarte tú?
Vamos.
Lo más cómodo, porque no sí, comparte pantalla. Slides. No. Claro, sí, sí.
Grande, lo llamo.
Los slides. Te envío un correo. Bueno, eres parecido. Sí, te envío un correo para que me lo envíes.
Ah, muy bien.
Sí, te lo voy a enviar hace
Ok, muy bien.
a todos los speakers de...
Para subir el tono, ¿no?
¿El qué? Sí, para subir el tono. O bueno, podéis compartir. Si queréis hacer como un círculo que es de el enlace a la web y compartir lo me envían. Os envío un email, sí. Vale. Vale.
No, voy a la página.
Ayer creo que veníais
Ahora sí.
Ah, perdón, ya lo he visto.
Ah,
No, no. O sea, vale.
Difícil después de
Menos mal que no entiende, no vaya bien.
Y ahora será automáticamente
El problema es que siempre tiene slides muy pesados.
El problema.
Es un problema, sí.
¿Para quién? No lo sé.
Una cosa.
y eso de todas más si queréis.
Bueno, tenemos que subir aquella cumbre. Sube corriendo ahí, una mochila cargada.
Ahora quedan 2 cerros más.
Eso es.
Aquí es donde atrás.
Ahí lo tenemos que cruzar aquel laboratorio. Y llegaremos a Inés.
Porque yo recuerdo también que entonces de la charla
Voy a poner algo mío.
y era una charla de 60 ahí hay que subir la hora por el tema que tenemos
Cosa seria.
puede el terror.
Vídeo.
Voy a comprobar que está el el se lo pone en las orejas. Vale, se ve bien. Sí,
Hello.
no, si es más bien se podía venir.
¿Me han mandado los papeles?
Sí, bueno, me han mandado aviso. Pero tenía que decir que no lo había hecho antes. Yo lo puedo.
No.
Darle ahora ahí.
¿Cuándo? No. No funciona. I had a Russian friend and I text 1, 2, 1, 2. Medio fuerte. Que no cuando
Ah, ¿es el Sherman? No, sí, me llevo 2 días. Yo quiero eso. No.
So hello everyone, welcome to the third morning session. Apologies for the delay, but it was the fault of the speaker. And our first speaker today is José Beltrán Jiménez. He's an expert in scalar vector theories and those things, and cosmology.
So you're making up everything today.
Yes. And today he's going to tell us some things about dark matter mechanisms through supersymmetric things. Okay?
Or not.
Or not. So, Jose, whenever you want.
Okay, thank you. Can we minimize this also?
Oh, yeah. You can, well, you have to do it on your computer, yeah.
No, this is fine. Okay, George. So yeah, thanks. Thank you, Gonzalo, for this fake introduction. Yeah, I was going to say that I'm very happy to be here in Valencia. It's always a pleasure to come here because I have very good friends, right? And yeah, so I'm going to talk about these things. I'm lying a little bit because I'm not going to talk about supersymmetry, except for the very last slide, maybe. And I'm not going to talk a lot about dark matter either. And I'm not going to talk about anything that has to do with electromagnetism. So it's all a lie. But then somehow it all makes sense, I hope. And so this is a work that I've been doing in collaboration with Dario Bettoni and Philippe Brax. He was in Salamanca with us until September. Now he's in León, not very far away from Salamanca. And Philippe is in Paris. That's the word, yes. Okay, so this is what I'm going to talk about. The main motivation for studying these scenarios is that so in the universe, why do we only consider gravity? And this is because it's a long-range interaction. And the question there that I wonder at some point is that if there could be some other interactions that are long-range that could play a role in the universe. And this is what I'm going to talk about today. And within this scenario, this von infrared magnetism is something that comes about very naturally. and with it, this cosmological setup, I'm going to study Newtonian cosmology. So this is the disclaimer because I think this is the modified gravity session. I'm not going to modify gravity at all. Not only that, but the only place where I'm going to talk about gravity, I'm going to use Newtonian gravity. So not even GR. Sorry about that. And then I'm going to describe how universe with dark matter that is charged under this dark electromagnetism evolved and how that could have an impact on the Hubble tension, and if we could explain acceleration with this scenario. And then I'm going to study the linear response of dark matter halos. This is perturbations around spherically symmetric objects. And here we obtain some nice results. But so this is the part of the talk here, where not even the speaker knows what he's talking about. I have some doubts. I hope you can help me to verify that, because I know there are some experts here in the topic. So maybe you can explain to me why we are obtaining some of the results, and especially this relation with supersymmetric quantum mechanics, because we can define some ladder operators, some conserved charges, and that has some relation with some of the results that we get. Okay, so let's get to the point. Cosmological forces. As I said before, gravity governs the large-scale dynamics of the universe. And why is this? It's because gravity is long range and it's universal, so it couples to all the particles. And then the question, again, is if we have other long range forces in nature. And you all know that we do. Right? Actually, the Mark Marx, you know him, he complains because in the degree of physics, we have 2 or 3 subjects for electromagnetism, and we don't have one single subject for gravity. Only in the very last, like an obstatic subject, we have GR, gravitation, something like that. I hope this will change because now we have gravitational waves, we have black holes, so it's becoming much more important. So this is for you to decide the subject, the plan of the degree, to take that into account. Anyway, so yeah, we have electromagnetism, but electromagnetism is not relevant for cosmology. And why is that? And this is because the universe apparently is electrically neutral. So all macroscopic objects tend to neutralize, and then the electromagnetic forces are negligible. So they don't play any role in the cosmological evolution. But we could pose the question, and this is what I'm doing here, if there could be some dark electromagnetism playing a non-trivial role. The idea here is we have dark elements, dark matter in particular. This dark matter could be charged under some dark electromagnetism, and then that could play a role. Because if we assume that all dark matter particles are identical, so we only have one type of charge, then we have a repulsion between these charges, right? And this will play a role on cosmological scales as well, because now we don't have this neutralization. But then there is a complaint that we don't spoil the whole stellar formation process. So if we add an additional repulsion between dark matter particles, that will modify the formation of structures, galaxies, dark matter halos, and all that, right? And then, if this was the case, we should have seen this already. Do you agree? You do. The only one. Okay, so what is the catch here? Well, this is where I'm going to explain how to get around these apparent problems. So let's try that matter out. And for this, let me go back to the Brownian electromagnetism. Marcel already told us about this yesterday, and there are some experts. Gonzalo, as you have worked on this. You have your wormhole solutions and all these things with this, no? And somebody else? Well, some people here have worked on this Brownian electromagnetism. So the original idea was to sort of regularize the self-energy of the electron by introducing these non-linearities in the Maxwell action. So, well, you can write it like this or in these two alternative ways. And the point here is that if you have an object, a point-length particle or a spherical object, and then you go very far away, this is the electric field, then the electric field is the same as sigma. So when the particles are far away, you have the usual 1/r potential or 1/r squared force. But as you get closer to the object, then these nonlinear interactions will start becoming relevant. and then at some point you will deviate from the Maxwellian behavior. And the deviation is such that the electric field saturates at the position of the particle, and it remains finite. You can actually solve analytically this the profile for the electric field, and you get something like this. So as I said, at very large distances, this is very small, so you get the usual result, and at small distances, this is this dominates over this, and then this R squared, they go away, and you get lambda. So they all saturate to this scale lambda. Okay, so this is an illustration of what is happening. If you have the two charges that are far away, and far away, I mean the distance between them should be larger than what is called the screening radius. And this screening radius is the scale below which the nonlinearities become important. Okay? So if they are far away, they behave like in Maxwell theory, but when they come close together, then these nonlinearities start having an effect, and then the electric force between them is screened. Okay, so you don't have the 1/r squared force. This is for different charges, and this is for the same charge. This is not special of Born effect. This actually happens for any nonlinear not anything. Say any sensible nonlinear electrodynamics. Okay. If you consider some function of these two Lorentz invariant scalars, then you have the same phenomenology. You have that you can solve it. If you neglect particle components, you can obtain the electric field by inverting this equation that is algebraic in the electric field for an arbitrary distribution of charges. So when they are far away, you have the usual Maxwellian behavior, but when they are close together, then you have this screening. Something that I like to point out is that despite having these nonlinearities, classical nonlinearities, it's a good quantum effective field theory because the quantum corrections will come in at the scale that is parametrically controlled by this scale lambda. So here I'm calling capital lambda, but it's the same. While the classical nonlinearities will depend on the charge of the particle that you're considering. So this is similar to what happens for GR, right? So classical nonlinearities become important at the spatial radius, if you want, but there the EFT is still good DFT, so quantum corrections are still more, and then only when you get to the Planck scale, the quantum corrections are important. So you have a range of scales there where you can have important nonlinearities for the classical solution, but quantum corrections are under control. Here is the same story. If you have an arbitrary distribution of charges, then you get that far, they behave as in Maxwell. Then you can draw this sort of screening scales or regions. And what is interesting is that because one might expect that if all the charges are below their respective screening radii, then everything within that radii will be screened. But actually, there will be holes in the screening region because there will be some points where the forces compensate, and then they become small again, and then you get again the Maxwellian result. So that means that even if you are inside, so remember that I have in mind the universe. So this means that even if you're inside the galaxy or a cluster, there might be points where you could test these additional forces, where the forces are compensating. Of course, we don't know where these spots will be, but for instance, if you go from the Earth to the Moon, at some point you will see these spots where you could test these additional interactions. Okay, so this is for general quantization, but Born-Infeld is special. And it's special because of certain properties. Electromagnetic self-duality, causal propagation. There are exact finite energy solutions. It also arises naturally as the low energy limit in string theory. I'm not going to discuss any of this. The only thing I want you to remember is that it has causal propagation and absence of shock waves and Weber fields. This is what makes this theory exceptional. Okay. I want you to remember this because then we will obtain some additional special properties for this, and this will be linked to this property of Born. Okay. Okay, now let's include gravity, and as I promised, I will do it in a Newtonian way. So nothing here. And now if we have two particles, massive with a charge, they're matter particles, Then we will have the usual gravitational force, and then the additional electric force between them. And then, well, you see that I can write these two forces like this. We have defined this 1 over ky. K is the Lagrangian, and ky is the derivative with respect to F So in Maxwell is 1, and in other theory it will be whatever. And I'm keeping this general because all nonlinear dynamics have the same behavior, and is that this k goes to 1 at large distances. So if this goes to 1, it means that this is has an effect. Essentially, it reduces g by the factor 1 minus beta squared. But when you get closer to the object, this goes to 0, and then this becomes this becomes 0, and then you recover only Newtonian gravitational force. So this means that if you have dark matter particles and they are within the screening radii, they will only feel gravity, and only when they are very far away, they will start with the extra repulsion. Okay. Well, this is what I just said. With the far away, they will see this effective Newton constant. This minus sign here is crucial because it means that you will have, of course, a reduced Newton constant. Because you have extra repulsion, so the force will be smaller. And when they are close together, the effective Newton constant will be the standard one, the usual. Okay. Now, so now I'm going to use this to describe the cosmological evolution. And what I have, I go to this. What I have in mind is a homogeneous distribution of dark matter particles. Okay, so at high redshift, so in the early universe, the universe is essentially homogeneous, and this means that all the particles will be sufficiently close together, so the extra repulsion will be strict. So there won't be any effect at high redshift. When the universe evolves, then things start collapsing. You cluster dark matter, you start forming halos, and at some point you will have these clusters, these halos, and then they will be sufficiently far away from each other so that the extra repulsion will have an effect. And this is something that happens at low redshift. So only at low redshift you will be sensitive to this extra repulsion. Okay, this is the general idea. How do we do this in practice? So if we're interested in low redshift, where the universe is dominated by dust, then the Newtonian approach is sufficient because pressures are small. So then what I'm going to do is I consider this homogeneous distribution of dark matter charged particles. I'm going to do this Newtonian cosmology approach, I guess you are familiar with. Okay. So then what I do is I arrange my dark matter particles into spherical shells because the force is spherically symmetric. And then for each shell, I compute the evolution. This is Newton's law. The evolution of the radius of this shell. Okay. And then of course the acceleration is just given by the force. And in this case, we have the gravitational force and this electric force. So if we start at some t star time with some initial radius r star, then at some time t, we have an expanded shell. It will depend on the initial conditions, but we are assuming that initially we have some co-moving motion of the particles. So then, if so this was in Lagrangian coordinate, as you know, it's much more convenient to work with Euclidean coordinates to describe the large-scale structure of the universe, because then we can introduce the scale factor, that is the position, so the radius of the shell divided by the initial radius. So when we do that, we recover this equation. We just rescale. And then the important thing here is if we don't have this extra repulsion, this is 0. Okay, and then here, if we assume that initially the profile is constant, then if we have a given mass within a certain radius, this mass will be conserved. So at any time, the mass within this shell will be conserved because you don't have transference of mass between different shells. And then in that case, what you have here is nothing. Well, this is m, this is r minus a, this is the density. And if this is constant, then you see that the dependence on r star disappears from here. And this means that all the shells evolve in the same way. And this is standard result that in Newtonian gravity we have co-moving motion. That's why we can describe the universe with one single scale factor. Okay, but now we have this extra repulsion, and this extra repulsion will depend on the spinning scale. So by the way, this is a consequence, of course, of conformal invariance of the 1 over r potential. or Maxwell or whatever. In Maxwell, we will have the same. It will be a constant. But if we have these nonlinear interactions, then the nonlinear interactions will break this conformal invariance. And this means that at some point, some shells will start exiting the spin ingredient, okay, and then they will start feeling the extra repulsion. And then they will evolve differently. So you will break the comoving motion. Okay, so this means that even if you start from a homogeneous distribution, at some point you will generate an inhomogeneous distribution. Okay, now let's solve the equations. Well, I guess you know that you can integrate this equation once just by multiplying by some a dot and integrating, and then you get the conservation, the energy conservation equation, which is the Friedmann equation. Usually, you only get this term here, and this will be the spatial curvature. That is the potential energy, the gravitational potential energy of your shell. But now, since you have this additional electromagnetic interaction, you also generate an electrostatic potential energy. And this is going to contribute to the spatial curvature of the shells. And this is something that you will generate only when the repulsion starts being effective. So only when the shells start exiting the spinning gradient. Okay. I think this is the only relativistic slide I have. And is that if you want to do this properly, then you should consider these Lemaitre models, where the line element is given by this, and this is very difficult to solve. I don't think there are numerical analytical solutions. There are some attempts to solve some simplified scenarios numerically. Even that is not trivial. Maybe for the numerical guys, it is obvious, but to me, this is very difficult. So I didn't even try this. I just wanted to point out that this will be the way to do it. And also, because if you're familiar with these LTV models, in those LTV, usually you put by hand the profile of the density of the void or whatever you want to describe, and then you solve for these functions. Okay. Here, you get this inhomogeneous profile naturally, because this will be generated from the evolution of the vector potential that you have. Okay, even if you start from a homogeneous distribution. Okay, enough for this. These are the lessons. I solved this numerically with Mathematica. Not very sophisticated, but it's nice. So you see, this is the mass within the shell. You see that the mass is conserved. So there is no cell crossing, there is no transfer of mass. This is what I was telling you. And this is something that you need to check, because the inner shells exit the screening radius before. So that means that at some point, there will be an inner shell, so some shell, that will start feeling the repulsion, and then they will start accelerating or moving faster because there is repulsion, while the external shells will still be within the screening radius. So there is a chance that the inner shells will catch up the outer shells. And then this shell crossing, non-shell crossing condition that I was telling you about might be violated. Okay, and this might happen. Born-Infeld seems to self-protect itself for this from this effect, and I think this has to do with this absence of shock waves for Born-Infeld electromagnetism and causal propagation. Anyway, so it seems that nothing very special is happening here. You have an expansion of the shells, but here I'm plotting the evolution of the density and the pressure of the shell. And you see that initially we have this uniform homogeneous distribution, but at the end, the density towards the edge of the distribution is higher. So this means that you create a void in the center of the distribution. And this makes sense because they start exiting the screening gradient, then they will start, as I said, they will start being feeling the repulsion of the inner shells, and then they will start stacking all the shells towards the edge of the distribution. So that's why you get this sort of void towards the center. Okay. Maybe it's more clear here. Yes. So here you see the evolution of the different shells normalized to the innermost shell. And then, well, this is the scale factor. Let me go here, maybe this is more clear. You see that all the shells are going the same way, with one single scale factor. And then you see that the smaller shells start exiting the spinning radii, and then they start evolving differently. And the bigger shells will exit at later times. Okay. And this is the region where the shells are crossing the screening radii. And this is where the inhomogeneities are being produced. Asymptotically, you see that the comoving motion is recovered. And this is more clearly seen here in the Hubble factor. You see that they all have the same. This is the transition region, and asymptotically, they all have the same Hubble factor. Although you have generated an inhomogeneous universe in the process. Okay. Asymptotically, this is what type of universe? Well, since this is generated by the presence or the generation of this spatial curvature from the electrostatic potential energy, this will be a curvature-dominated universe. So essentially, you go from a dust-dominated universe to a curvature-dominated universe. And this is the evolution of the electrostatic energy that I was telling you about. So it grows, and at some point it saturates. Okay. And this is only for dark matter particles, but of course in the universe we have baryons. So what happens when you add baryons to the picture? And this is what we are doing here, because this dark magnetism is going to couple only to dark matter particles. We don't want to mess up with baryons. Otherwise, we will have problems with colliders and solar system tests and all these kind of things. And I don't want to do that. I'm very conservative. Yes, so now we have the charged dark matter and the uncharged baryons. This is easy to model. And then you see that now, because baryons will continue their motion without the extra repulsion, then they will be left behind the dark matter evolution. And the dark matter evolution, once the electric repulsion is active, they will start evolving, expanding faster. But this has an indirect effect on the baryons, because then the mass within each shell of baryons will be modified. So then you will modify the gravitational force for the baryons as well. It will be a smaller effect, but you see here that you still have an effect. Okay, so this is green is for dark matter, and this is for the baryons. Okay, so even if you don't have direct coupling between the dark electromagnetism and baryons, you will have an effect on the evolution of baryons as well. This could be seen as violations of the equivalence principle, because you would see that cosmologically baryons and dark matter particles behave in a different way. But of course, this is not a violation of the equivalence principle. It's just that you have an additional interaction. Okay. Now, let me tell you a little bit how this scenario could tell you something about the Hubble tension. It was already mentioned by Paula first day. She's not here. And let me, so the general idea here is that, so if you remember, the Hubble tension has to do with the fact that when we measure the Hubble constant with high redshift probes like the CMB, you get a lower value than the one you obtain when you look at nearby objects, like supernovae, surface, and these kind of things. So the idea in this scenario is that this could be explained because when you look at high redshift, you are looking at structures that are still screened. So you don't see the extra repulsion. When you look at nearby objects, then these objects might be in the regime where the extra repulsion is effective. So you will see an extra repulsion between these dark matter halos or galaxies, and this will increase the separation, the speed between these objects. And this will give you a higher value of the Hubble constant. Is it clear, more or less? Okay, so this is what I'm illustrating here. So within this scenario, so if this is the center of the distribution, we would be here, and then we will be looking at the galaxy at some point here that is in this shell. And then what we want to measure is the receiving velocity, that is just the velocity in the direction of the object. So it's given by this. And then from here, you compute the observed Hubble factor as the receiving velocity over the distance. Okay. Doing this, I learned something about standard cosmology. and is that if you look at this, so this is also what we do in cosmology, in visual cosmology. And if you do this, you look at this geometry of the problem, you will say, okay, this quantity must depend on theta. No? Of course. But when we measure the Hubble constant, that doesn't happen. There is no theta dependence. No, it's the same. Doesn't matter where you look at. Well, it turns out that this is a consequence of, again, of the comoving motion. Because when the motion is comoving, then, well, I don't have it. Then V is proportional to the distance for all the shells, and it's the same, if you want, factor. And then that will cancel the angular dependence. This is what we see here. But in this case, because we have this extra repulsion that breaks the comoving motion for my invariance, then you will see an angular dependence for the Hubble factor. And here I'm plotting the one that we would observe divided by the cosmological one. That will be the Hubble factor for the outermost shell, the ones that are very far away. So the ones that will be probed by the cosmological observations. And then if we look at distances very far away, then we obtain the cosmological value, of course. But then as we start looking at closer and closer objects, then the Hubble factor will start increasing because we will start probing a universe that is curvature dominated, and that expands faster than a dance dominated universe. And on top of that, there will be an angular dependence, because since we are starting probing this region where there is no comoving motion anymore, we will see the homogeneities, and this will introduce an angular dependence for the Hubble factor. So this will be a sort of smoking gun for this scenario. Now you will see here that this is 1.5. This is a variation that is too big. This would be in conflict with the observation. But here I'm not including dark energy. What happens if we include dark energy? Well, it's very easy, because then in the Newtonian equation, we can include the cosmological constant just by adding this step linear in R, okay? And then we can solve the same. And then what happens is that once lambda kicks in, the dark energy, then all this story goes away because lambda dominates everything, and then it starts entering the comoving motion dominated by lambda quickly. And then what happens is that this growth of the Hubble factor, as we look at nearby objects, will be smaller because dark energy will suppress this. And then with the help of dark energy, we can get the 20%-ish difference that will be compatible with detection that we seem to observe. Okay. Are you convinced of this mechanism?
You have 3 parameters.
You have?
You have any-
Yeah, one. The scale of the nonlinearities. That's the one you have to fine-tune to get it right. Yes. Okay, so just a few words about the shell crossing, because actually my initial idea was completely different. So my idea was that, well, the story will be the same, but then what I thought that might happen is that when you get this cluster universe, then the extra repulsion will start making the universe expand faster. And then I thought if this could explain the accelerated expansion without any lambda. Okay. That doesn't seem to be the case, because so even if you have shell crossing, this is what I'm illustrating here. Well, you have shell crossing, you have the mass that is constant, but the best I could get for this is an expansion, a Hubble factor that goes like 2/T. This gives you a little bit of expansion, of accelerated expansion, but not enough. So maybe you can hook up a more contrived model to make it expand faster, blah, blah, but I don't like proceed. So if it doesn't work in a natural way, I just move on. But then this Hubble tension came about, and I thought, oh, maybe we can use it for this. Anyway, now this is for the, I was going to say homogeneous, but like the background cosmology. And now what we wanted to study is, okay, you have a dark matter halo here, and then if you put a dark matter halo here, how the first object reacts to the second object, okay? Or how the dark matter halo reacts to the whole distribution of dark matter in the universe. Okay, so now what we want to do is to study perturbations around a spherical symmetric object. And as a first approach, I'm going to use the point-like particle. Okay, so this is what I'm doing here. How am I doing this time?
20 minutes.
20 minutes.
Well,
That's fine.
15,
that's good.
so that we can finish 15, so that we can give
So,
for time for
20.
questions. But
Okay.
it depends if you want questions.
No, particularly.
Okay.
I think so far everything is clear, no? That's nice. Yes, so I don't know if you're familiar with this thing, but what we are doing is that. So we have this point-like particle that will generate this profile for the electric field. And then I want to study the perturbations in the electromagnetic field within this nonlinear electrodynamics, okay? So then what we do is we compute the quadratic action for the perturbations around this background, standard. And then what you get is this type of expression, okay? And then the first thing that you want to look at is the propagation speeds. And now here we have three types of propagation speeds, because you can have a mode that propagates radially, and then the electric field and the magnetic field propagate in the oscillate in the angular directions. So that means that the propagation speed will be the angular over the angular, ky over ky. This is one. This makes sense because if you have a photon propagating in the radial direction, it will not be sensitive to the electric field and the magnetic field will oscillate in the orthogonal direction, and they will not be sensitive to the profile of the electric field. So it makes sense. Now, for the angular modes, you have two types of perturbations. So you propagate in an angular direction, and then you can have the electric field propagating in the radial direction and the magnetic field in the angular, or the other way around. The electric field in the angular direction and the magnetic field in the radial direction. And then we have angular field in the angular direction and the electric field in the radial direction. This gives you this propagation speed, or this magnetic field in the radial direction over the electric field in the angular direction. And this gives you this propagation speed. So you have two propagation speeds for the angular modes. I'm plotting here the profile for the propagation speeds for Born-Infeld and for this quadratic correction here. Okay. Now here you will see something fun. Here I'm also plotting this screening factor. Remember that this 1 over ky is what gives you the screening of the electric force. Okay? It goes to 1 at large scale and to 0 at small scale, which is what we see here. Okay. So this is the screening scale. So you see that outside the screening scale, all the propagation speeds go to 1. That's what we do. But below, then they go subliminal. And this is important, because if you do the same for a scalar field, you get that they go superluminal. And this, not necessarily, but might pose a problem to come up with a Wilsonian UV completion of the theory. In this case, this is fine. So no conflicts with causality and these kind of things can arise. But there is something interesting, and is that you see that for Born-Infeld, this seems to go to 0. While for this other modification, it goes to a constant. This is that's what. Does it make sense? It's a coincidence. No, of course. There are no coincidences. Okay, let's try to understand this behavior. Well, the radial modes propagate at the speed of light, so not interesting. But now let's see if we can say something about the behavior of these propagation speeds from some more fundamental things. Okay, so if we want to have a screening active for this model, then that typically requires that the second derivative of the Lagrangian should be positive. But if this is positive, y is essentially e squared, so that's positive. So that means that this, so if I divide by 1, this is smaller than 1 because this is bigger than this. So this means that the screen branch is naturally compatible with subluminal propagation. As I said, if you do the same for the scalar field, you get the opposite, that the screen branch is incompatible with subluminal propagation. And only when you go to the non-screen branch, you can get subluminal propagation. For this second propagation speed, I'm going to use duality invariance. I know some of you are familiar with these things, but Are you all familiar with duality invariance? So essentially a rotation of the electromagnetic field. So a linear order. So actually you can compute an equation that will tell you if a given nonlinear electrodynamics is duality invariant. When you specify for the perturbations in that linear order, you get that this relation should hold for having duality invariance. Okay? Then if you plug this relation in the propagation speed, you will see that the propagation speed goes like 1 over Ka squared. And this is actually what we saw here. What is it? Here. This is 1 over K. If you count, this is 1, and this is 10 to minus 4, and this goes to 10 to minus 8. So it's precisely that. So this is nice. This is nice, but it's not nice. Because that means that as you get closer, since this goes to 0, then the propagation speed of this mode goes to 0. And this poses a potential strong coupling problem. Because if the propagation speed goes to 0, that means that the energy associated to exciting spatial gradient will be essentially 0. And this means that with little energy, you can excite large spatial gradients. Okay. It only happens at the position of the particle, so might not be a fatal problem, but nevertheless something to keep in mind, because this might be problematic. Now, instead of this Born-Infeld theory, I'm going to consider this how is it called? Born-Infeld dice, Max, whatever. Are you familiar with this Lagrangian? No. Who is? You are. You are. Good. Okay, so it's a horrible Lagrangian. I agree on that. But it has some nice properties. And is that this is an additional parameter, and if you take it to 0, then you recover Born-Infeld. Okay? And if you take this lambda to infinity, you get this mod max theory that is the only nonlinear electrodynamics that is both duality invariant and conformal invariant. And this is important because it means that asymptotically we will still have the Maxwellian behavior, 1 over R squared, because remember this is a consequence of conformal invariance. But you will have a correction depending on this parameter gamma. So you will have a sort of screen charge, a global screen that will not depend on the gradients, okay? On R, as I was saying before. Okay. So now I'm going to study static perturbations. So for that, I take the electromagnetic equations and the Bianchi identities. Now, the interesting thing is that if you perturb, well, this is what you get. But then you see that you have this rotational equal to 0, and this means that I can introduce these two scalar potentials to describe the electric and the magnetic perturbations. Okay, and now we do what do we do? Here's for start. We have the spherical symmetry configuration. So we expand in multiples, we compute the equation, and blah blah. This is what I'm going to save you all the details. This is very standard. It's boring. This is what you get. So for the polar sector and for the axial sector, you get an equation for the multiple that essentially depends on a given mass that depends on the Lagrangian, specific Lagrangian that we are considering. Okay. Well, here I'm plotting the masses. So again, for very large scales, here you see that they go to the Maxwellian, that is this dashed line, and then below the screening radius, the masses are different from the Maxwellian behavior. Okay, so now let me focus on the polar sector. For this, it's very interesting that if you rescale the potential and introduce this coordinate, you can write it in this nice way. And of course, you all recognize this equation, the hypergeometric equation. I'm sure you all have studied this equation. No? Yes. So this is very nice because then the solutions are very well known. We have for the asymptotic behavior of the solutions. We know the analytic properties, so we can have take a look at some book on special functions and have all the properties. Now, what we want to do is to compute the polarizability. How do you do that? Well, the idea is that you put your object, you turn on an external field with some multiples, and then you see how the object reacts. Okay. And now, what of course, you have to impose some boundary conditions. What we are imposing is that in Born field, the next property is that the electric field remains regular at the position of the particle. So we are going to impose that the perturbation also remains regular at the position of the particle. Okay? When you impose that, this is the solution, and then you expand asymptotically for very large distances. And then this is what you get. This is essentially the amplitude of the external field that you are turning on. And this is essentially the decaying tail of the object. And this is the external field that you are plugging in. Then the reaction is the ratio of the decaying over the growing mode. So this is the polarizability. You can compute it from here, and you get this expression. Okay? This is the polarizability. And now, what do you do? You plot it. We only want plots. And then you plot it, and you get this. And then something funny happens. And is that you look at the dipole, the quadrupole, you look at L equals 3, and you see nothing. And then you look at 4, and you see something, nothing, something, nothing, blah, blah. So you see that all the odd multiples have vanishing polarizability. And this means that if you introduce an external field with those multiples, the object will not react. It will not be affected by this external stimulus. Okay? And this is interesting. I mean, this is not common. No? No. If you do it for the axial sector, you do the same. You compute the regular solution, you compute the, now this should be called magnetization, something like that. How do you call it? Let's call it magnetization. But now you see that while here, this gamma parameter in this horrible arrangement that I wrote before doesn't appear, here it does appear. And then there is a continuous dependence on this parameter, and then you get this. Okay? So here, nothing special seems to happen, except for these points. But now, if you go to Born-Ifeld, then this simplifies dramatically, and then if you plot the polarizability and the magnetization together, you see that the magnetization precisely fills all the gaps that have vanishing polarizability. So now you get vanishing magnetization, but for the even modes. Okay? And then asymptotically, they all align along this 2 to minus L asymptotic behavior. And this is where not even the speaker knows what he's talking about. So I don't have an answer for this. I don't know why this happens. I don't know if there's, I feel there is some underlying reason for it, but I don't know. So if any of you knows the answer, I'll be happy to hear it. But now, here, this resembles the vanishing of the log numbers because you've seen this before. This is what happens when you put a black hole and some external stimulus. Then you see that there is more dramatic because all the linear response parameters vanish. These are the so-called log numbers. So you put the black hole and you put some other black hole nearby or whatever external field, then the black hole will not react. Okay? And so this looks very similar to that. And then recently there have been some nice works trying to understand this behavior, and they saw that they can understand this in terms of some hidden symmetries, and they can introduce some ladder structure, some ladder operators that connect different multiples, and they can use that to generate a whole hierarchy of conserved charges and some interesting things. So we thought that maybe something similar might happen here, and that's what we did. I was telling Adria yesterday, so I tried to do the same. So I said, okay, what are these guys doing? I'm going to do the same. And then I didn't find any ladder operators. And only at some point after being a bit desperate, because I thought there must be some ladder operators, I tried something more radical. And then at the end, what I found is that there is not only one set of ladder operators, but two. So in this system, we have two ladders. One that is given by these operators, particularly illuminating, looking at the expression, but you have this commutation relation with this Hamiltonian that is essentially the kernel of this Hamiltonian gives you the solutions for the multipoles. But then you see that instead of connecting L and L plus 1, as usually happens, it connects L and L plus 4. It's something I have never seen before. And then this, what we call small ladder, connects L and 3 minus L. So this only connects the first 4 multiples. But this is very nice because we can connect the first 4, and then with this, we can jump steps of 4. So we can connect all of them, no? So this is quite remarkable. And then if you look at this and you put L equal 1, 1 plus 1 is 2 times 1, 2 minus 2, 0. You see that the constant mode is a solution. So you see that this is a conserved charge for the dipole. That is, well, this is the generator. For the monopole, it's less trivial to see, but you can also see that there is a conserved charge given by this. And then, so since we have a conserved charge for the monopole and the dipole, so for the monopole, we have a conserved charge. And then we use the small ladder that connects the monopole with L equals 3. And then we can go all the way. And for the dipole, we have conserved charge for L equal 1 with this letter 3 minus 1 is 2. That gives you a conserved charge for L equal 2, and then you can go all the way up with the ladder operators. Okay? No. No. Yeah, life is always tough. This is a main lesson of this talk. And when you try to do that, then you find that these ladder operators have some non-trivial kernels for the space of solutions, which is something also strange to me because usually ladder operators do not have kernels in the space of solutions. You can move around all the modes freely. Now, what happens is that this ladder operator for A naught, we can always split the solutions into the regular solution at the origin and the singular one. And then it turns out that the regular belongs to the kernel of this raising operator, which means that you cannot raise the regular solution of the monopole to L equal 4. This is very disappointing. Okay. But everything funny happens, and is that the kernel of this low-end operator is in the singular sector. So there is a way to connect all of the multiples, and is that if you start from an arbitrary multiple, you can go all the way down till here, and then you hit the regular solution. But then the regular solution is not in the kernel of A naught. So you can use A naught to go to the regular solution of the monopole. So you cannot go up, but you can go down. And this is the connection that you find between all the multiples. Okay. And this is nice because the ladder operators connect regular solutions to regular solutions and singular solutions to singular solutions. Okay. And for the dipole, something similar happens. You have some material kernel, but again, you can go from an arbitrary multiple to here to regular. No, this is the other way around because now the kernel is here. Now the non-trivial kernel is in the singular sector. So now for the regular sector, you can go up, but you cannot go down. Okay. And something interesting is that we have these towers, and these two towers are precisely the ones with vanishing polarizability. And this can be connected to the vanishing of these conserved charges. Okay. Can be connected in the sense that you look at the things and you see that they are the same. But I don't know why this happens. Okay. Now, for the axial ladders, you can do something similar, but then you have this dependence on gamma. And then what you find there is that if you try the factorization of this type, then you see that only when n is equal to 4a gamma, you can have these ladder operators. And n and gamma are independent. So the only solution is gamma equals 0, n equals 4. And then, if you remember, gamma equals 0 is precisely Born-Infeld. So only for Born-Infeld, you can find this ladder for the axial modes as well. And this is very remarkable. Here is where I ask you to remember what I told you in one of the first slides, that Born-Infeld is the only one with causal propagation and absence of subwaves. And I think this is the key point here, because one might be tempted to say that this is because of duality invariance. 2 minutes. Good. That this is because of duality invariance. But all the models, so all the values of gamma are duality invariant theories. So this cannot be because of that. And what actually singles out Maxwell Born effect between the nonlinear electromagnetism is the causal propagation for arbitrary backgrounds. Okay, so there must be a connection there. And yeah, only for Born effect. And then it turns out that when you plug gamma equals 0, n equals 4, you also find a small ladder. And then you can do something similar. So I know this diagram is horrible, but it took me a couple of afternoons to make them, so I feel the urge to. I'm lazy, but not that lazy. Sometimes I work. Okay, so now the promised supersymmetric part of the talk. It turns out that you can write these supercharges in terms of these ladder operators, so the ones I found out, and then you can write this supersymmetric Hamiltonian that satisfies this algebra, and this is the Lie superalgebra SL11. So there is a supersymmetry here, and this can be seen very nicely because if you introduce this variable and you redefine in a non-trivial way the equation of the multiples, you get this, and you of course recognize this. Actually, it's not the first time this equation has appeared here. This is the Schrödinger equation, the eigenvalue problem, the Schrödinger equation for a post-Taylor potential. I mean, I get it away here. So you can look at the Hamiltonian of the post-Taylor potential, and you see that they have these arbitrary parameters. So now you only need to solve the equation. This equals that, this equals that, blah, blah, blah. You do it, and you find 4 cases. And then you have these 4 associated post-Taylor problems. You can compute the, so this is a very well-studied quantum mechanical potential. So you know the eigenvalues, you can use non-results to obtain the values of L, and then you get these 4 associated problems. You see that this is precisely the 4 different multiples that we need to specify to have all the solutions, regular solutions for the hierarchy of multiples. Okay, because once you specify 4 with another operator, you generate all of them. Okay, and it turns out that these 2, 1 and 4, are the only ones. So these are the ones with vanishing polarizability, and those are the only ones with a normalizable ground state. So this relates the normalizability of the ground state of this potential with the vanishing of the polarizability. What does that mean? I don't know, but it's a fact. And now, lately, of course, we've been doing this for Born effect, but there is a very cousin of this, and this is the Dirac-Born effect theory, that this is for a scalar field. It's much more, so it's easier because it's only scalar field. And if you look at the static and purely electric configuration, you see that B is 0, B is 0, and the 2 Lagrangians are exactly the same. And this is nice because for BBI, we know that there is a nonlinear irregular symmetry, because this can be seen as the symmetries of a brane in a 5-dimensional Minkowski space. So we have nonlinear translations and in the additional boost in the 5th dimension. So this has a nonlinear symmetry, and this allows to unveil a symmetry for the static perturbations of the purely electric configuration. This is my last slide. So the story is that you can do the same, and you find similar things, and B equal 4 arises as a special case. This is all. Thank you.
Thank you, Jose, for your talk. Is there any question or comment? Next time you will be the chair.
Have you tried about the Hall tension, have you tried with the other cases of the Lagrangian? You see the corrections that you get? I guess they are very small. But
I haven't tried that one. I tried other ones. So it's not, so DBI doesn't play, BI doesn't play any special role. You only need to have this screening. The reason why we use Born-Infel is because you avoid in a natural way the shell crossing. And for other models, this might not be the case.
But the cell crossing is just a technical problem.
yeah,
Yes.
so it shouldn't be like it should be a problem at the level of observation technology. Where it will
Well, if you start having cell crossing, the phenomenology will be different. So I did it for Born-Infel, but there's nothing special regarding the Hall tension
Yeah.
of Born-Infel. Yeah, it could be for any other.
Any other question? Yes.
I got a bit confused with regards to the screened and unscreened regions. So at the beginning, the Born-Infel the potential gets modified at small distances, and I didn't follow very well how then the repulsive force arises and whether the repulsive force is at small distances or large distance. So,
Yes, so the idea is you have an object here, and then that generates an electric field, and the electric field. So this object has an associated screening scale. Okay, if you are outside and you put the charged particle there, it will feel the 1/r² force. If this particle is inside, then the nonlinearities are important, and then the force is clear, meaning that it's smaller than what you would expect for 1/r².
that scale is put in by hand, or
This is determined by the scale lambda that regulates the nonlinearities and the charge of the particle. So it's similar to the Schwarzschild radius of a black hole. Depends on the mass of the object and G.
then the repulsive force is small distances or large distances.
So it's when the objects are outside their respective screening radii. Yes.
Okay, thank you.
Okay, we have one more question.
Your main assumption is that dark matter has this electromagnetic behavior that is different from standard Coulomb attraction forces. Are there bounds? This is just because I'm not aware of it, but are there bounds on standard matter having this kind of Born-Infel behavior? So are there bounds on the parameters that can exclude this kind of corrections to standard matter electromagnetic interaction?
Yes. So
Which are?
so I don't know the latest one. I guess if lambda is anything above 110 dB, you should be safe. Essentially, so you can look at photon scattering, for instance, from there to the strain. But there are other constraints also from cosmology.
Thank you, Jose. Thank you for the questions. Our next speaker is Maria Jose Guzmán, and she is going to tell us about the feedback from Marisa. Symmetrical values.
No, pero es porque es en la radio.
How do I pass the slides? Okay.
¿Tienes esto? ¿Certi? ¿Pero?
Okay, hello everyone. Thank you for being here and having me here. I have 17 minutes to talk about this topic. Actually, this is not modified gravity, but general relativity in a different formalism. But it has applications to modify gravity, of course. So the idea is very basic. I hope I'm able to convey a very basic idea, and the idea is that we have these reformulations of general relativity in the teleparallel formalism, and these theories are called the teleparallel equivalent of general relativity and the symmetric teleparallel equivalent. And my idea is that some things, due to certain properties of these theories, it is possible to have new insights in numerical relativity. And the reason for that is because there are boundary terms that affect the Hamiltonian of the theory. I mean, the theories are equivalent at the level of the equations of motion, but not at the level of the canonical structure. So the Hamiltonian constraint are slightly different. And I think we can exploit these differences in order to have, for instance, a better, more efficient numerical relativity. And why not to have modified gravity out of it? So that's the main idea of my presentation. So now you can leave. But obviously I will give more details. The talk is loosely based on these three papers, but I will only be talking about this paper that came out recently, and then just giving just saying some words about these other papers. So since I was relying that Jose will talk about the trinity of gravity, now I have to introduce it. But if you remember Alejandro's talk, then you will remember that there are properties of the connection, which are the torsion and the non-metricity. So for building out teleparallel theories, we will consider not only the metric, but also a linear connection. And instead of taking this connection totally arbitrary, we will put some restrictions on it. And to put these restrictions, we need to know the properties of the connection, and these properties are the torsion, which depends purely on the connection, not on the metric. So you take just the antisymmetric part of the two last indices of the linear connection, and the non-metricity, which is a property not only of the connection in this covariant derivative, but also it involves the metric. So this is the most general connection, and a linear connection can always be decomposed in three parts: the well-known Levi-Civita, a part that only has torsion, and a part that only has non-metricity. So now, our teleparallel frameworks are obtained from this main condition, this main position that the curvature is of the Riemann tensor that you compute with the most general connection is 0. And that's already teleparallel. So that is called, if I'm not wrong, general teleparallel framework. But then in this general teleparallel framework, you can either impose the non-metricity 0, which leads you to the, sorry, I think here it is, it is inverted. So Q equals 0 leads you to the metric teleparallel, and T equals 0 leads you to the symmetric teleparallel. That's what when you do the slides with the sleeping. So just have to remember that you have these three properties of the connection, and two of them will always be zero, and you will have some interesting framework, which is interesting because you will get once you take these scalars that you can build from these geometric properties, you can build a Lagrangian that gives you the Ricci scalar up to a boundary term. So in principle, well, I am focusing now in the symmetric teleparallel framework. So in this framework, we have curvature zero, torsion zero, torsion zero, and the only object that we have is this non-metricity tensor. So we build some scalars out of this non-metricity tensor, and after computing the curvature of the full connection, imposing it to zero, we are left with the curvature of the Levi-Civita connection, the non-metricity scalar of this non-metricity tensor, and a boundary term. So you plug this into Lagrangian, and you obtain that this integral of this R is equal to the integral of this cube up to a minus sign, and this is integrated out. So at the level of the equations of motion, everything is the same, but this boundary term starts playing some role when we go to the symplectic formulation of the theories. But now an important point is that what happens with the connection when we put these impositions for imposing non-metricity zero or torsion zero. So the connection is not fully trivial or not fully determined, but there are some. It took some time to realize, although it's quite an obvious issue, that the connection. Well, here I'm writing the spin connection, but you can relate it with the linear connection through the derivative of the tetrad framework. So here, in the metric teleparallel framework, this connection can be written in terms of matrices belonging to the Lorentz group. In the symmetric teleparallel framework, you can write the linear connection as the double derivative of a set of four scalars that represents a coordinate transformation. So somehow the connection is can be written in terms of let's say fundamental fields that you just put in your Lagrangian, like extra fields. And when you do it this way, you obtain a genuinely teleparallel framework because you know that these connections are teleparallel. Another way of imposing these conditions is with Lagrange multipliers, but I won't focus on this approach because, well, some other colleagues do it that way. I maybe don't like it. So now, after I have this, I specify the connection, I specify my scalar, non-metricity scalar, I do an ADM decomposition, and this is the standard thing for the metric, because in symmetric teleparallel I have a metric and this set of four scalars here. So the thing is how to do an ADM decomposition. In the metric, it's super easy, it's just this very well-known thing. But what do I do with the extra fields, these psi fields? So do I decompose them or not? And in the metric teleparallel framework, do I decompose these Lorentz matrices or not? So a better idea is just, if we are considering the equivalent theories to general relativity, I will just choose a gauge where the connections go to zero, and I don't care about this ADM decomposition. This is true when the theories are equivalent to general relativity, but for f of q or f of t theories, like you have seen in Alejandro's talk, f of q, probably this is not a good idea because this psi a has these double derivatives in time, and it seems to me there is some non-trivial dynamics there. But since now I'm focusing just in general relativity, I just want to do this, and I just make the connection go to zero. It is still teleparallel. And now an important point in this 3+1 decomposition is how do I define the extrinsic curvature? Because now my connection is not the Levi-Civita connection, but this symmetric teleparallel connection. So the traditional definition of the extrinsic curvature is this, equation 8. However, with the symmetric teleparallel connection, this will be this connection. So the covariant derivative of a normal vector will have an extra contribution. So if I wanted to build some extrinsic curvature out of this connection, then I will have something different compared with the extrinsic curvature of general relativity. So although you can see in the literature some approaches, 3+1 approaches based in this general connection, maybe they're not so correct because you get these extra things that you don't know how to interpret. They kind of don't live in this 3+1 foliation. And moreover, if you have torsion, then the antisymmetric part of the extrinsic curvature is different from zero. So what do I do with that? It's not very nice. So the definition of the extrinsic curvature should be this, number 8. And then once we do this 3+1 split, we obtain after integration by parts, main integration by parts, and some arguments, you obtain the action 3+1 action for general relativity, because this is just the typical standard part of general relativity, and then some splitting of the three-dimensional Ricci into three-dimensional nometricity and something that looks like a boundary term. And actually, in my first paper, this last paper, I said this is a boundary term. Well, it's not, but you can do some integration by parts here and have some term that doesn't have second-order derivatives of the fields. Because if you remember this Q was the covariant derivative of the metric, but in the coincident gauge, the covariant derivative is the partial derivative. So this term has derivatives, first-order derivatives on the metric, and then with another derivative, you get second order, but then somehow you're not exploiting the advantages of these symmetric teleparallel frameworks, which is your action can have only first-order derivatives on your metric. So I just thought, and I argue, that a better approach is to just make an integration by parts and just work with things that have first-order derivatives, which simplifies the Hamiltonian constraint for instance, some spherically symmetric distribution of the intrinsic metric. So why one could be interested in this? Because at least for numerical relativity approaches, one of the simplest examples that one can make is, for instance, like some spherical symmetry, like a black hole with some scalar field, and you can model this numerically. And I think one of my interests is to develop like the numerical, let's say, see what is the impact of these changes in the Hamiltonian and the Hamiltonian constraint in numerical relativity in symmetric teleparallel and metric teleparallel. So that's why I'm interested in this and just showing this example. And for this intrinsic metric, the Hamiltonian constraint in the symmetric teleparallel, here there are these terms that come from the integration by parts of these terms with the nometricity traces. And here I was a bit sloppy and I didn't put this, but this, you have to believe me, it only has first order derivatives on the metric, yeah? So here I was sloppy because here this K represents the independent components of the extrinsic curvature, which for this spherical symmetric metric, there are only two independent components. So this Ka and Kb, and also there are when you write the Hamiltonian constraint, there are also the function a and b appear on it, but also its derivatives with respect to the radius. So these variables db and dA, they are just the derivative of b divided by b. I didn't put these definitions, I'm sorry. So this is for the Hamiltonian constraint for symmetric teleparallel equivalent. And you only observe these first order derivatives in the functions. But for general relativity, you have these second order things, like in particular here, which probably for numerics is not very nice in the sense that every time you have these derivatives, you have to include another Runge-Kutta, and then my hunch is that it will be simpler, but it remains to be proved. Later now I have students working on that. And if not, then we can move to something else. So yeah, I was trying to answer the questions. So why is this important? I believe that these symmetric teleparallel or metric teleparallels can provide a richer framework to understand general relativity itself. It seems to me the boundary terms are very important for the formulation of the numerical relativity issue. And why do we want numerical relativity? Because what it seems to me is that at least I have been contributing in, for instance, finding black hole solutions in FOT gravity, and at some point there are just no exact solutions anymore. So somehow we probably have to resort to numerics. The problem is like things like FOT and FOQ, they have their own problems too, related with the strong coupling, and then one has to define what is the strong coupling, if it can be formulated a certain sector of the theory that is healthy, and maybe in this sector we can have, for instance, hairy black hole solutions. So I believe like it's not only FOT and FOQ, we can also build like a what's the name of this? Scalar torsion or scalar non-metricity theories, which I suspect the claims of strong coupling could not be applied so easily, maybe. Maybe you can say something different. But the thing is that these theories, such as Hondensky or stale quadratic gravity, like FOR, they also have these hairy black hole solutions. And when it turns out to predictions, like predicting a merger of two black holes, if you have just the same solutions of general relativity, you will just get the same predictions. So you will not get anything different. And what you want is that your gravity theory behaves differently in the strong gravity regime. So depends for what you build your theory also, because if you just want it to be some cosmological, let's say, a new dark cosmology thing, then yeah, this is not important. And yeah, so that's why I think it is important. And these are my future prospects. Extension to scalar non-metricity. And also, I was just talking about symmetric teleparallel, but actually, I think teleparallel equivalent is more interesting because there, the metric is not the fundamental variable, but it is the Firvine or tetra field. And in that sense, you have more freedom to play with the equations of motion. And for instance, if you would like to tackle the issue of strong hyperbolicity, in the sense that you make the 3+1 decomposition of your equations, and then you try to prove that it is a strongly hyperbolic system of differential equations. I think with the teleparallel framework, it will be maybe some tricks that you can do there to make the proof simpler. And yeah, so that's my interest for now. And now, since I think I have some time, I have a little bit of advertisement. So next spring in 2024, we will have in Estonia, in Tartu, the course Selected Topics in the Theories of Gravity 2. It will be a mock course, so you can take it online. If you're interested in this, in learning our approach in these topics. And the course will be given by Damianos, Iosifidis, and me. And also another piece of advertisement is that every June since 2017, University of Tartu and the Laboratory of Theoretical Physics have been hosting the very nice workshops, Geometric Foundations of Gravity, which is like a big workshop, like 60, 70 people, and another small teleparallel metric affine gravity workshop. So I think this year we have to do the small one, but still you are welcome to visit us there and having very nice discussion. And also a couple of PhD positions will be open next year in autumn 2024. And this will be more or less the topics that the students will get. So if you're interested or you know someone who's interested in going there, just let me know. Let's stay in touch. And although it might look like going to Estonia is something like really hard, like life is hard. Yeah, life is hard, but it's also beautiful. So this was last week. There was a record for November -21 degrees. And this is one of the beautiful things that you can see there and you cannot see here in Valencia, for instance. Or also this, like really, really beautiful. So thank you very much.
Thank you, María José. Questions, comments? Anything about the Strongcat links? Okay, so we don't have snow, but we have a good beach here and paella, excellent food.
I provoked Gonzalo.
María José, I was wondering, the way you were explaining, you were fixing the gates before computing a Hamiltonian, right?
Yes, I was doing that in the equivalent, because in that equivalent, the spin connection, it's included in the action up to a boundary term. So that's the reason I can do that.
Okay, so in general, you cannot, but in this case, it works.
I mean, in f of q and f of r, sorry, f of q and f of t, it said this, you know, this approach of the coincident gauge that since the connection is, you know, pure gauge, you can just fix your system of coordinates that the connection is 0. Yeah, I think there are divided opinions. Some people just say that you cannot just do that. You have to prove first that that this connection, you know, that these fields are totally gauge. Or some people will say it's quite obvious they are Stuckelberg fields, so you can just get rid of them by choosing the gauge.
Yeah, I mean, I would say I'm more of the second opinion, but I don't know much about how these things work. So I was wondering whether this would have problems in the Hamiltonian structure in the sense of what Fernando was explaining, that maybe some of these consistency conditions then are harder to enforce, or maybe even not possible. But
I'm more on the team of doing the full. Well, you mean like for this teleparallel for the equivalence?
Yeah, like I would agree that these are clearly Stuckelberg or purely gauge, but I don't know if you can just get rid of all of this before going to the Hamiltonian, or in general you have to compute it from the whole thing and then get rid of them.
I think I will go for that. I would go for that approach. It is a bit harder because these connections that I was showing, they impose some extra primary constraints. Actually, for this, we have already worked a couple of years in, you know, deriving the primary constraints derived from these extra fields and then showing that they're first class. So I think in that case, there is no problem. But now I think the same proof has to be done with these 4 scalars. And in the second paper that I showed, we formulated the primary constraints. But I think we still have to prove that they are first class. And they don't pose any problem. Some people might say it's obvious. I think it would be nice to do the full approach. I think for that we need a little bit more of research. Yeah, thank you for the comments.
So we don't have time for more questions. Thank you, María José. Okay.
No, pensaba en un último.
Sí, sí,
Okay, so next speaker is Andrea Donini. So he's going to tell us about a new method to measure deviations from Newton's law.
Hello, everybody. I'm happy to be here. Actually, I'm here in Delphic, but to be here in an audience that is far from my usual public. And I also have a disclaimer because I'm not going to talk about modified gravity. Although, actually, one of the reasons why I'm here is that precisely those kind of models could offer some options of models that can be tested by this kind of approach. So that actually this is an advertisement in the sense that we had a theoretical idea some years ago, and we are now moving to the starting of an experimental phase. So we are basically looking also for motivation to test this in some particular part of the parameter space that we can address. This work has been done in collaboration with several people. Some of them are still here, like Sergi there. And these are the people with which we are trying to move from the theoretical phase to the experimental one. Okay, where should I go into? I should move manually.
No.
Okay. Okay, the main motivation for going into this is that I'm coming from particle physics, and I know that the standard model is not the end of the story. When I talk of standard model, I mean standard model of particle physics, not of cosmology. And this is because there are many experimental evidences that tells you this. For example, we do not understand what is dark matter. There should be something that may be called dark energy. We have no idea of how neutrinos get a mass. In the standard model, they are massless, although we know that they are not. And also, we don't know why there is no antimatter in the universe. So these are evidences that tells you that the Lagrangian of the standard model cannot explain these things. As a consequence of this, there are other things. For example, the second one is that if the standard model is not the end of the story and there is a more fundamental theory, then you should explain why electroweak processes appears around this scale, and some observable are not touched by some higher scale. For example, the largest of them could be the Planck mass. And so this is called the hierarchy problem in particle physics. It's basically the source of a huge amount of models that has been proposed to go beyond the standard model. Most famous of them is supersymmetry, Technicolor, whatever. Another important point is that, of course, the standard model cannot explain quantum theory of gravity. It's not included, and that could be a very important step beyond. So basically, because of this, I entered this field by studying one modification of the standard model that is putting it in more than 4 dimensions. Okay, so this is an idea in which some of this extension, like string theory, implies that there are more than 4 dimensions. Some low energy approach is putting the standard model in, say, 5, 6, whatever. So you get a mixed, you are abandoning a bit the realm of particle physics, you are playing a bit with gravity, not so much, and you try to stay there. Okay, so this is why I entered this, because once you accept that you have more dimensions, maybe you want to try to test the gravity and see which are the effects of those dimensions. And the 2 ways of testing gravity is going to very far distances in astrophysics, in cosmology, and whatever, but also going very short distances. So down to which scale you believe standard gravity. If there are, for example, more dimensions, will you start seeing deviation from the attraction proposed by Newton, and then that's why instead of testing the standard model by the standard way, that is using colliders at very high energy, or going to precision physics by looking for rare processes, we decided to try to see what happens if I look to deviation from some well-established law, and in particular, we want to test the Newton law. So the Newton law that tells you that the attraction between two bodies goes with the square of the distance between them. Okay, so my motivation was because I was studying extra dimension, but then we understood that this goes beyond that. There are more models that can have impact on this particular relation. So how experimentalists parameterize this? Usually they write a potential that is an effective potential in which you have 1 times this that gives you the Newton potential plus corrections, and they are cast in a Yukawa-like form. This is just a matter of convenience. You have a correction on top of 1, and since the effects are negligible at the distances that you are testing, you assume that they will increase at some particular scale. Actually, this is an effective assumption, but for example, if you go to extra-dimensional models and you do an expansion in your parameters, you end up with an exponential potential like this. So, for example, I can already tell you that if I just put the standard model 5 dimensions or 6 dimensions, or whatever, and I try to study gravity in this framework, I can also tell you which is alpha. For example, in flat 5-dimensional space, alpha is 1. If there are 2 dimensions, it will be 2, and so on and so forth. If you go to modification of, if you put more dimensions, but also you make curvature in this extra dimension, then this parameter will change. But this to tell you that, for example, experimental model can be cast in this particular case. What are these 2 parameters? So alpha is a coupling that you are testing, could be positive or negative, depending on the sign. It will be an attractive or a repulsive correction. Most of the plots are given for positive alpha, but in principle, also the other part of the parameter space could be studied. And lambda is the particular scale at which you should start to see something. Okay? So, which is the state of art? This is by 2020. I've not seen any newer result because improvements are very slow in this particular field. This was the improvement going from 2016 and 2020. So you see, well, 2016 was in this region, but for the same collaboration that was testing this, it was from 2007 to 2020. Okay, so any of these bunch of lines comes from different groups. They are not so many. They have their methods, and I will tell you how they study this, but the results are basically for alpha equal to 1, that, for example, is those that you should test if you are in just in 5 dimensions, and that's it. Standard general relativity just in 5 dimensions. The bounds on the scale is that is less than 40 microns. Okay, so up to 40 microns, gravity is 4 dimensions. For example, for very large alpha, the bounds is a bit better, in which case you can have a large alpha. For example, fifth force, quintessence, these kind of models imply usually large couplings to solve the particular problem for which they are proposed.
Yeah. Question. So the effective potential that you show is effective in 4 dimensions.
Yes.
You have quantification.
Yeah, whatever you get, in the end, you have to, I mean, you are in 4 dimensions. You live in the experimentalist live in 4 dimensions. So your probe should be manipulated in 4 dimensions. So this is the effective 4-dimensional potential that you get. Okay. The other realm that could be interesting is the is the one of very small alpha. So this zone is not very well tested. So bounds are 1 millimeter. Okay. How they get this? Well, basically, in the end, they are all variation of the torsion balance. So this is the best way to measure this. So in the end, you are okay. The method is with a torsion balance and so on and so forth. But in the end, you are testing the attraction between two bodies. Okay. So what you are testing is the module of the force between the two bodies with respect to what you expect, that is the Newtonian one. So you get 1 plus eventually the correction. Okay. I'm sorry, this would be the potential. In the force, you have another formula. This should be the derivative of that. But let's understand that by this way, you are testing 1 against a correction. Okay. Of course, this correction is exponentially suppressed. This means that you are far away from lambda, from the critical lambda. This is very small. So it's a small number on top of 1. Which is the problem? Well, imagine that you have backgrounds. Backgrounds could be whatever, systematical backgrounds or things that you are not, that you should take into account and modify your measurement. What they are doing? Well, basically, they are introducing a correction to this one. Okay, this could be not a perfect knowledge of the Newton constant, whatever. Whatever you put would be something in this form. So you have 1 small things that you are looking for plus correction that you have to compute. Now, which is the point? That is that the torsion balance method, or that if you want, the method in which you approach bodies and you try to test the absolute value of the force between them, is affected by a lot of electrically induced backgrounds. For example, imagine that your bodies have a residual charge, then you get a Coulomb attraction. If you have neutral bodies, but with a dishomogeneous distribution of charge, which is the case, you have dipolar attraction forces. You can have van der Waals forces because of they are not local objects, and so on and so forth. Now, what is common to all of them is that they give you a 1/r potential. Okay? All of these backgrounds that are the dominant one when you get to micron size distances gives you 1/r potential. So basically, they are precisely this kind of correction. Okay? So this is why it took 13 years to improve from the previous bounds to the new bound, because you are going from 100 microns to tenths of microns to 10 microns, the tenths of microns, and then you start to get electrical stuff. Okay, so you have to shield your bodies, you have to invent ways to remove them. So what we want to do? Well, we want to use a theorem that 150 years old, that is called the Bertrand theorem, that tells you only potential that goes with 1/r or r squared gives you closed orbits. Okay, in the case of 1/r, you know, the planets around the sun orbit with ellipses, or they could have other trajectories like hyperbolic or parabolic trajectories, but the ellipses, of course, are closed orbit. So a body moving around another one will go again in the same place after a certain amount of time. However, this is strongly dependent on the particular form in which the potential depends on R. So what happens is that if you include a correction to the potential that are not going as 1/r, you get precession, and this is what happened, for example, to Mercury. The sun is so near to Mercury that the general relativity correction gives you a dependence on the distance that is not 1/r, and instead of getting a closed orbit, you get precession of the orbit. Okay, this is the very well-known result. So what we want to do? Well, we want to do the same in a microscopic size distances. So this is a plot in which we have a planet. The planet is of 10 to the minus 5 grams. Is something like 30 microns of radium. And there is a satellite. The satellite in this particular case is a couple of microns of radius. is 10 to the minus 9 grams, but it's independent, the orbit will come out the same. They are at a distance of 20 microns. Then we put some initial conditions, so no radial velocity, only angular velocity, and we put it into orbit. Okay. If you are Newtonian, you will do this, the red one. And if you have correction, in this particular case is for an alpha 0.2, you get precession of the orbit. Okay, so the idea is, if I see the precession, I'm seeing things that are not 1/r. Okay, so I forget completely of the electrical variables. They can be there or not. This will not affect the precession. They will only affect the time it takes to the satellite to go back to the same position. Okay, so it will go to the same position, but slower or faster depending on the electrical correction. But if there is precession, this is something that is not 1/r. Okay, so this is the idea. We proposed this in 2016. It's an idea to get rid of the main backgrounds. Are there other backgrounds? Of course. For example, you have this object and you have electric Casimir. This gives you a force that, if you compute the Casimir for spheres, is 1/r². General relativity, in the case of Mercury, it was the dominant modification. It is 1/r⁴. There is also gravitational Casimir that is 1⁶. So we parameterize the Newtonian potential with a set of operators that introduce correction. This Q2, the number goes with the force. So this goes 1/r² in the force. These are the electrical stuff. That is a correction to 1. Then there are other objects. Okay? Other objects that can be computed, but they are sublime with respect to this. Okay, they have to be taken into account. For example, if I have this Casimir and the value of the operator is, say, large, this is the Newtonian period that is constant because of the third Kepler law. And if you put this correction, the period in which after some revolution can change and depends on this coefficient. This means that this coefficient should be taken into account. So the idea is to start the experiment far away, let's say 1 millimeter, and then you test this kind of quantities going a bit nearer, and then you can fit your coefficient. Once you know that these coefficients are under control, they will not change. They change only because of the dependence on R. So the coefficient is fixed. Then you can go nearer and subtract. Okay. Then we have also included now in a second step the viscosity of air. Of course, all the previous computations were done in vacuum. This is very nice, but as soon as we get in contact with the experimentalists, they say, okay, but this is not in vacuum. So we included the dissipative force. The dissipative force will imply that the satellite after some point will start to crash onto the planet. And so you need a certain amount of vacuum. This is increasing the vacuum. Say that here you are at 1 bar, so a 10 to the minus 8 dilution, 10 to the minus 9 dilution, 10 to the minus 10 dilution. So in this particular case, with no subleading backgrounds, you have to go to 10 to the minus 10 dilution of the air that I have here in order to reproduce the Newtonian result. But this is because the setup was not optimized to get rid of effect of air. The planet is very large and the satellite is very small. In order to reduce the factor of air, I can put the satellite a bit larger, because if it's larger, it moves differently in air. The impact of air is more relevant. If I'm very big and I'm moving here, I will not see that there is air. If I'm a dust particle, I will not move because I'm stopped by it. Okay, so we can re-optimize all of this. And this is the experimental setup that we are planning to do now. So a bit larger planet, 5 and 10 to the minus 5 grams. Probably should be made of platinum, but gold is okay also. The size is something like 80 micrometer. The satellite would be made of plastic, basically. Is a bit larger. Before I was considering 10 to the minus 9 grams. Now it's 10 to the minus 8. This is to reduce the effect of air. It's a bit larger. Why this particular choice of the material? Well, I'm here, and what's happening if I leave this, I will not do, is that it will fall down because of the Earth. So of course, if I put the planet and I put the satellite here, the satellite will go down instead of going around the object. So I have to remove the Earth gravitational field. Either I go into the space, but the idea of this experiment is you should do at home. So it's much better if you can do it. So I have to remove the Earth's gravitational field by some way. And the idea that we are testing now is magnetic levitation. So I need something with the magnetic susceptibility that is like this in order to make the satellite levitate and stay there, okay? I need some pumping, but by having to change the characteristic of the setup is a bit less. So this, for people doing vacuum, is called moderate vacuum. So it's not a strong requirement. And then I will put cameras. At the very beginning, we were testing just the time it takes to make a full revolution. So it's a very simple observable with a laser that tells you to trigger to take a time measurement. But then, of course, if you can follow the movement of the satellite around the planet, it's much better because you can have a much more refined field. Okay. So with this setup, we have a very good resolution on the position of the center of mass of the satellite. The satellite is 16 micrometers and the resolution on the center of mass is 1. So basically, you know the position of the satellite. Okay, this would be the setup. Below there is the vacuum pump. Then there is a vessel in which you will introduce your objects. So here you will have the vacuum. In the very center of the vessel, there will be two magnets. Here, one is red and one is blue. Okay, and this is the front view between the two magnets. The magnets actually are commercial ones. So actually, you can go and buy something like $50, not more. And they are this size. Of course, I mean, when you go to the realistic stuff, probably you have to adjust a bit. But up to this moment, the most costly things are the cameras. The steel are the order of some thousand of euros, not more. So you are talking about 10,000 of euros between this stuff, something like that. Okay, this is the magnetic field inside the two magnets, and the effect of the gravitational field is that your satellite fell a bit. I mean, you can reduce, of course, by increasing the magnetic field and move this a bit up, but it's not necessary. As long as you are a bit away from the magnets, you have no border effects, and you are safe. By increasing a bit the magnetic field, you can put this. These sides, I mean, for those that there is something like 300 microns. This is the active region of your laboratory. The real active part is 300 microns. Orbits are around 100 microns. Okay, and this is what you will see. The time it takes to do an orbit is 1 hour and 40 minutes, more or less. Okay, so this satellite moves in a couple of hours around your planet at a distance of 100 meters. Okay, so it's very, very slow. It's not even the Earth Moon, it's much slower. Okay, these are the size scale. So this would be the planet and this would be the satellite. Of course, because of their size and your precession, at some point, maybe they can collide. So at that point, you should stop making your measurement. But you see that you have many orbits before that happens. And we have seen that in 3 orbits, we have plenty of data. So more than 6 hours are irrelevant. Okay. This is including those backgrounds that I told you. The Q3 is the most important one. This is the Casimir effect, the electrical Casimir effect. It's very important to say that with this particular setup, one is platinum with a metal, and the other one is plastic as an insulator. The Casimir effect should induce a clockwise precession. Whereas for alpha positive, you have counterclockwise precession. Okay, so the effect of the Casimir is less important because it's in the other direction with respect to use. Okay, these are the setup, and this is the result. So in green are the present bounds. In blue, it was the setup optimized in vacuum. That was better, of course. And in green is the realistic one with the air. So what happens is that we are still able to increase a lot with respect to present bounds. In particular, for alpha large, we increase a factor of 2. The alpha large is the region in which torsion balance experiment could improve still a bit, because the correction to 1 is large. In the intermediate region, that is, say, that from here to here is the region interesting for extra-dimensional models. We can increase some factor, okay? And in the low region, we increase order of magnitudes. Basically, all of this is a gain. So any model that will imply a correction to the gravity, to the Newton potential that has a very small coupling could be tested a lot. I mean, can be tested in this way. Okay, see, so conclusions. We are saying that looking at the orbit of a microscopical size object is better than just putting the two microscopical size objects one near to the other, because you have a smoking gun of something that is non-Newtonian. Dominant backgrounds are irrelevant. Subdominant backgrounds can be studied before approaching the very short distance regime, and is not complicated from the point of view of the setup. We are now going to the experimental phase. So basically what we are doing now is to buying the objects. First of all, we are looking for companies producing micron-size plastic stuff, and then we have to learn how to take it, move it, and things like that. This will be done by people in San Sebastian. And the second step is that we are also, of course, going for the magnetic levitation. There are alternatives. Still, the group in San Sebastian is also looking for optical levitation. They should define a defocused laser in order to get a region of 300 microns in which you get a flat plane, basically. Usually, optical levitation is done for very small objects. So you have a very focused laser that brings things up. In this case, we want that the object can move, so we need to defocus the laser in order that you get the flat region. That's why we are going for magnetic levitation for the moment, in which we have already done the simulation. And then we have to understand how to put the satellite into motion. The idea is that you can just put a pulse laser on it. It should work. The same people that are looking for optical levitation are also looking for the intensity of the laser that you need to give a kick to the satellite. Alternatives are many. Whereas on our side, the theoreticians, we are now including the vibration, in particular vibration of the planet, because there could be an earthquake, or there could be an autobus passing by, or just the experimenter that is this. And we've understood by preliminary study that more or less all of this situation can be taken into account, and there is no problem. Okay, the most important result is that the planet should be fixed rigidly to the point in which it is. Okay, so this we have to understand how to do it, but if it's more or less rigid, you can think, how do you say, a brochette. So the picture that we have in mind is like a brochette. Okay. So since it's rigid, it cuts very large fluctuation that could get into resonance with the movement of the satellite. If they are very fast, you average of them and the reading. And that's it.
Thank you, Andrea, for bringing this interesting experiment to this meeting. We have time for a very quick question. So, I choose.
Good, thank you. Very nice talk. Actually, we have two, but the first one is: do you have enough control on the shape of the magnetic field to guarantee that the force is precisely in the vertical direction?
Yes. This was done with a professional program simulation that is called CONSOL, given us by engineering. And you see that the region is so small that we are basically guaranteed that the vector field is parallel. So we have control on that. We have also included in our simulation a bit of a drift, and it also doesn't change. You can also move, as you told me, increasing or change by going from these magnets that are permanent magnets to electrical magnets. You could also change a bit things by moving a bit. You could also reduce this homogeneity of the field. And you only have to be safe enough to be a bit away from the border, because there the surface could be wiggly, and then just around the border you could have small effects. But as soon as you are, I mean, saying a number, but 50 microns away from the border, everything is under control.
May I ask a very quick one? Bismuth is also very diamagnetic. Have you thought of using it?
Which one?
Bismuth.
For the moment, we just were testing this particular material because people in the material department told us that was the one that usually is used for magnetic levitation. But we are open to, we are testing because we have to buy them and to see how to manipulate. For example, in principle, we are talking about spheres, just because you think of spheres when you think of planetary systems. But can we actually make a sphere out of this particular material at this size, or maybe other materials could be better? So we also try to see if asphericity of the material could give you problems. In principle, my impression after working on this is that everything is so classical that can be solved. So it's you have not thought of this. Well, think about this, you include this in your equation of motion and you solve it. It's not, since it's not quantic. So we have included a bit of sphericity, doesn't make any problem. And maybe the satellite could also be a cube. Maybe. If it's better to cut, it could be. The Casimir effect will change. But I would not think that will change very much. So we have some control also on the Casimir effect, so we can include the temperature, we can include things. Okay.
So thank you, Andrea. Let's thank him again. Okay, since we are a bit late, there is the coffee break now. We will be back in 20 minutes. So this is 12:15. Okay? I will let you know.
Ah, vale, pero perdón, que también te me regalado una charla.
Creo que ha sido punto por punto de lo que se y ya con referencias a todo. Porque se dice
Bueno, sí, la solución de esa cuestión no hemos incluido la posibilidad que el segundo cuerpo sea una sección diferente. El estándar por sería anteriores a 2000. Pero, claro, modificaciones a los campos de estilo, como yo sé, claro, hasta cambiar.
Claro que cambiado.
Como hacían recién, no sé qué, mucho más de tema de ver que cuando haya más casos de gravedad, pero
Claro, claro. Claro, no, la pregunta sería de
la electrodinámica está a la distancia más grande. Pues la idea es de momento estamos pensando
Giulia, ci senti? Giulia.
Sì, ti sento.
No, perché il tuo nome sta tipo in prima fila qua, Giulia, Giulia qua, e quindi niente,
Infatti non so come toglierlo, questa cosa mi imbarazza un po', però va bene.
volevamo molestarti un pochino.
Ah,
Ciao,
ci sta. Ciao.
mi sono perso le tue slide. No, scherzo. Basta.
Tu arrivi proprio.
Ma tipo adesso voi sentite il computer che sta sventolando malissimo?
No.
No? Oddio, sento un po' male, mi sa, aspetta.
Così,
Mhm, sì.
microfono che è spento. No?
No, no, così vi sento, però dico l'audio mio è decente o fa schifo?
Vabbè, perfetto, è perfetto.
Ah, ok, no, perché sta andando malissimo, però sono contenta che almeno non si sente il ronzio. Ok.
Vabbè. Io vado al bagno.
dependent on the notion of distance and axis.
Yes, here yes, but not online.
Okay, is it working now?
Yes.
Okay, what is interesting is that when you have a metric affine, when you deal with metric affine approach, you can introduce, as we already know, interesting structures, interesting new quantities like homotheticity, torsion. And especially I want to mention this homothetic tensor. It turns out that it's not has a role in the conformal symmetry. I don't know if I'm going to show this, depends on time, but in principle, this becomes important. What is the homothetic tensor? It's actually the, with respect to the first two indices of the riemann, in general, we assume that you have anti-symmetry. This is due to the fiber bundle that you're taking. That in the fiber, you should have SO13. This means that they should be in an anti-symmetric representation. But if you relax in some way this hypothesis, and then you dynamically recover the symmetry, then you can introduce this homothetic tensor. Okay, just to set up the stage, I want just to mention what has been done before. Well, in the attempt to include electromagnetism into gravity, Weyl proposed this symmetry, proposed that the theory should be invariant under Weyl transformation. And this means that you have to add a Weyl field, so an additional gauge field, so additional degrees of freedom to the theory. And this Weyl field enters the non-metricity condition as the non-metricity tensor. Okay, this is the first approach by Weyl. But in particular, a key property of the connection in this case is that it is invariant under Weyl transformation. And this is the expression. So you have the Christoffel symbol plus these three terms that depends on the Weyl field. So you have invariance of the Weyl connection. This proposal has been rejected because it doesn't match with the notion of distance. It's not consistent with quantum assumption. In principle, this means that you have a dependence on the measure length of the space-time paths, and this is not possible. So it's been rejected. Obviously, as you already know, this turned out to be the first example of a gauge theory, but in this form has been rejected. So interestingly, in 1982, Hopko found a way to recover the metricity simply introducing restating the same symmetry in the context of metric of Einstein-Cartan gravity. So what he did, he said, okay, let's say that the Weyl field is the torsion trace. In this way, you recover metricity condition, but now the torsion is inside the definition of covariant derivative. So in some way generalized, but it generalized in the context of Einstein-Cartan gravity, not metric affine. Okay? And in particular, you already discovered that the gauge transformation of the torsion trace is nothing but an integrable projective transformation, that is this one. Okay, so everything was consistent. This all this setting was not followed in fact, when I started this research, I didn't know about this period. And so, which is the advantage to include the torsion in this way, to say that the torsion has a gauge meaning? First of all, by a integral projective transformation, the Riemann is invariant. Okay, then you can introduce a Stuckenberg formalism in a natural way by saying that these fields are propagating. Then you can explain how how the Planck scale is recovered, because the theory is not a scale, but breaking this symmetry, you set the scale, and you can assume that the Planck scale is the scale that you are gaining by breaking the symmetry. And moreover, you can model interesting cosmological scenarios using this symmetry. But there are two main questions that are still remaining. The first one is if there is any fundamental reason to introduce this new gauge field and this symmetry in the theory. And the second one is if you can encompass all these in a metrical fine framework. And we're going to answer to these two questions. But before that, let's analyze the parallel transport. So in general, you learn that the parallel transport is given in this way. Okay, you have the directional derivative of a vector is parallel transported if along the path gamma mu, if this quantity, the directional covariant derivative is zero. And by substituting into the vector, the tangent vector itself, you gain the autoparallel path equation. That actually is not exactly the geodesic equation because you are still you should be still in a metrical framework. But if you assume that you have metric compatibility, this is exactly the geodesic equation that is equal to zero. Okay, but if you assume that the length of the vector is not fixed, is independent of the notion of parallelism, then the equation changes. Because as you transport the mu, you have to transport in the same way lambda x d mu. So if you substitute this, you get another equation with a term that depends on lambda, where lambda in principle is an arbitrary function that describes the length of the vector along the path. The same happens for the geodesic equation or the autoparallel equation that gives you an additional term. So in the books, you find a way to cancel this term in the case of the geodesic equation by deparametrizing the geodesic equation. So you change the parameter, you reabsorb this. This is quite annoying because, first of all, you cannot do that for the parallel transport. Why not? Because this is reparametrization invariant. So this is the first problem. And the second problem is that once you reabsorb this term, you cannot change anymore the parameter. So the parameter is fixed by lambda. And so you lose the parameterization symmetry. So these are fundamental problems that it's not been solved before, and but there is a very easy solution. And the solution is that you can reabsorb these terms using a projective transformation. So if you assume, and it turns out that the projective transformation that you need is exactly an integrable projective transformation. So as you can see, the parameter mu that defines the projective transformation is the derivative of log lambda, where lambda describes the length of the vector. So in principle, if your theory has this symmetry, you solve the problem. And the fine structure is well defined. So what does it mean having this symmetry? This should be a gauge symmetry, an internal symmetry in some way. So, okay, the same happens with the geodesic equation. In this case, if you use the integral projective transformation, you recover the usual geodesic equation, but now you still have the parameterization invariant. Since every time you want to change the parameter, you can reabsorb in a redefinition of gravity. Okay, I didn't show you here, but it's a very old result that the parallel notion does not depend as an invariance, the parallel notion in a fine structure, as an invariance, that is invariance under projective transformation. So everything is consistent. I mean, the parallel transport is well defined in this case, but the price to pay is that your theory should be invariant under integrable projective transformation. So how to include this symmetry in a gravity theory? So the recipe is very easy. And it turns out that you can define a covariant derivative if you assume that your vector transforms in this way. So this is the transformation associated to this symmetry. So as you can see, it's a scaling transformation, but it's not any scaling transformation. This scaling transformation depends on the nature of the vector that you are transforming. So you have this factor that is weighted by n minus m, where n is the number of covariant indices, and m is the number of contravariant indices. Okay. So if you transform the vector in this way, and you transform the connection inside the covariant derivative through an integral projective transformation, then the covariant derivative is well defined. And so you discover which is the symmetry, but still you need to understand which is the gauge field. In the gauge field, the first thing is, okay, in particular, this symmetry, if you consider as the vector the metric, then you get exactly the Weyl symmetry. And so next step is to identify which is exactly the gauge field. In the gauge field, I mean, the first things you try to do is to take the trace of the integral projective transformation. So you get the trace of the connection, and you end up with something, a quantity that is not a vector. So the right identification is given by the torsion trace as predicted by Obuchov. Right? And the torsion trace is nothing but the vector part of the decomposition, reducible decomposition of the torsion. So it's basically this first term. Then you have a axial vector and the remaining degrees of freedom that are included into this Z minus 1. And so everything's fine, and you discover that you have this symmetry. So next step is, okay, now that you have this symmetry, and you identify the gauge field associated to this symmetry, what is the difference between this and the Weyl transformation and the Weyl approach? The difference is that now the gauge field is not added, but it is included into the connection. So this means that the symmetry is already your theory. You don't have to add something. Given that, you can build the theory, and but build the theory, unless it is a quadratic theory, that is the only one that doesn't need quadratic modified gravity. For other theories, since you have to contract the Riemann, you have to add a compensator that is a scalar field. And this scalar field should transform in a precise way that define a covariant derivative for that depends on the new field. So if you assume that the new gauge field and this compensator are dynamical, that means they propagate, you generate a Stuckenberg sector that is nothing but the kinetic terms of the gauge field and of the compensator. And in this case, this theory, and then you have a matte sector that you have to add. Anyway, this theory has a precise property that it is not minimally coupled. There is a coupling between the trace of the connection and the matter. So surprisingly, you can solve the connection field equation, and the solution, I'll show you what it is this. The connection is given in terms of this auxiliary metric, that actually is defined in terms of this new tensor. There is nothing but the derivative of the gravity sector with respect to the Ricci. You can solve for a very large family. There are the Ricci-based family. And you see that the torsion now is given in terms of the torsion vector. And this is a solution that comes from the dynamical equation associated to the connection. Okay, what is the difference now between what has been done before? That now you have a field equation even for the torsion trace. And this field equation is a change of paradigm, porque this means what? Because this means that the geometry is dictated by this linear field. In particular, I want to show you an equation that is quite interesting, since I have to skip something here. That is this one. So you can find, if you fix the gauge, you set phi equal to 1, you find that the curvature, the scalar curvature, calculated on the Christoffel symbol of the auxiliary metric, is given by the dynamics of this gauge field. So basically, the geometry depends strongly on this gauge field. And this means that you can model a lot of things in this way, and this is work in progress. And what we are doing now is try to model a cosmological, try to build a cosmological model based on this to justify phenomena like dark energy with a specific potential. Okay. Just to give you another example, okay, this is done with the simplest theory you can imagine. That is the conformal version of general relativity. Actually, general relativity conformal version is very easy to obtain. You just multiply by this phi the Einstein terms. So basically, you get Bremsdicke plus the kinetic terms. What is the problem to find solution of this theory? Is that basically when you go on shell and you generate the mass scale, you have to deal with a Procca field, as you can see here. So this F mu is the field strength of mu, the gauge field associated to the gradation. What you get is that you have to solve a theory that is basically general relativity plus a massive gauge field. But this gauge field is not the usual gauge field. This is a mistake that Weil as well did. This is not a gauge field because the symmetry of this field is compact. So it's something different that has never been considered before. And it's justified by the notion of the parallel transport, the existence of this field. So nobody knows the solution of this theory. How much time is that? Minutes. So just to give you an example, not more complicated example, it's very easy to generalize any metric, any Ricci-Basel theory. Take, for instance, the identity-spare Born-Infeld. You just have to add a coupling phi squared here in front of G mu, okay, to get a conformal invariant theory in this sense, in the sense of Weil transformation. And then, using the recipe that I gave, you can solve this theory, and you get the auxiliary metric, and you can go on exploring this symmetry to get some observable result. So it's very easy. Concluding remarks. The message I want to leave is that any metric of phi formulation of gravity should encompass conformal symmetry, by symmetry, let's say. That the field equation of the connection can be solved, and you have a non-trivial symmetry breaking a la Zuckerberg. Even in the simplest instance, that is the general relativity, when you make it conformal, then the geometry is not trivial and gives you interesting phenomena. And obviously, the new framework that we propose demands for the study to understand observational effects. So I'm working on the theoretical part, model building basically. So I try to push the story to the observations, but it's still work in progress. What about future developments? I would like to spend some minutes on that, but probably we have no time. And so, as I said, there are strong implications for cosmological models. We are working on that. We just, the main ingredient is that, the main point here is that the metric that you assume cannot be the simple Friedman metric Friedman the make Robertson work, but it has to be completely anisotropic. This is well known when you have a electromagnetic field as well. You need an anisotropic setting. So we are working on that. Then we are searching for exact solution of this theory. And this is interesting because finding exact solution for this theory has implication in holography. And then another point that is very cumbersome is how to include fermions in the treatment. And this point is very problematic because the fermions in the metric affine approach are infinite dimension. And then the last point that I'm mostly focused on, this last point, is how to search other hidden symmetry related to the remaining irreducible representation of the torsion. So what does it mean? So far, what we did, we found a way to include wide symmetry into any Ricci-based theory or metric affine theory, gravity theory. And we did that by identifying a part of the torsion as the gauge field. Can we do the same for the whole conformal symmetry? What does it mean? Okay, conformal symmetry has two meanings. In the gravity community, just the Weyler scaling, but actually the conformal symmetry, the complete conformal symmetry acts on the coordinates, not on the metric. So the point is, can we include the whole symmetry into the theory? And this is a work in progress. My reference, if you're interested in this line of research, is this paper that I published with Gonzalo Olmo and Gianfranco Padisi for University of Vergara. This proceeding where the field equation of the connection solved. Then I remind you this work of, and even this work of Dadic and Pons is quite old. Would be interesting to travel with. So thanks for your attention.
Thank you, Manuele. We have time for a short question or comment. No? Then, thank you, Manuele, again.
Yes.
Okay, our next speaker is Miguel Pinto from the University of Lisbon, and he's going to speak about non-minimal geometry matter couplings and their implications. Okay, yeah.
Can you hear me? Okay, thanks. So, hi everyone, my name is Miguel Pinto, and today I'll be presenting non-minimal geometry matter couplings and their implications for gravitational physics and cosmology. In particular, I'll be presenting an overview of this class of theories and also the works that I've been developing in the past several months. But before that, let's make sure that all people can understand what I'm going to talk about. So, apart from all incredible implications and predictions of general relativity, GR, the Einstein's theory, is at the core of the lambda CDM model, which is basically the standard cosmological model that assumes the universe as an homogeneous and isotropic universe modeled by the Friedmann-Robertson-Walker metric. The matter content in such a universe is basically the usual baryonic content, the usual baryonic matter, and two dark components, the cold dark matter and cosmological constant, with the latter being responsible for a late-time cosmic acceleration. But it is undeniable that there are some shortcomings and drawbacks in both GR and the lambda CDM model. For example, the lambda CDM model does not explain the true nature of both dark energy and dark matter. In addition, there is now an evident discrepancy between the measurements of the Hubble constant in late time and early time measurements, and this is called the Hubble tension. Moreover, and in a more theoretical side, we know that GR lacks uniqueness in the sense that there are other theories that can explain the exact same phenomena as GR, but by resorting to other geometrical quantities, in particular, torsion and non-metricity. And this is remarkably referred as the geometrical trinity of gravity. Okay, so this basically hints that maybe we need some new gravitational physics. And there are many ways to tackle these issues, but one possible route is modifying gravity, okay? And there are other physical motivations behind such modifications of gravity at large scales. For instance, the possibility of a more realistic representation of the gravitational fields near curvature singularities, but also to create some first-order approximation for a possible quantum theory of gravity. But how does one modify gravity? Well, according to Lovelock's theorem, a consequence is that in order to modify the Einstein field equations and therefore basically change how the gravitational interaction is modeled, we have several options. For instance, one can add extra fields to the gravitational sector, add more than second order derivatives of the metric, include non-locality, and add or remove extra dimensions. And this is basically how does one modify gravity. But now let me just talk about the particularly interesting class of modified theories of gravity, which are the non-minimal geometry matter coupling theories. Basically, in these theories, there are direct interaction terms between matter and geometry, contrasting to what happens in GR, in which basically the matter and geometrical sectors are completely separated. For instance, such a theory is given by the f of r Lm gravity, in which Lm is the matter Lagrangian. So there can be we can have some mixed terms between the curvature and matter. There are other examples such as these ones. And a very important consequence arises in such a theory, or such theories, is that the matter-energy momentum tensor is not necessarily conserved. And this has a direct implication, is that an extra force can appear, and this extra force can, at least in principle, be an alternative to dark matter. Of course, there are some other issues, but if you have some questions, we can leave that to the final part of my talk. And in fact, there has been a lot of interest in the last couple of years regarding this class of theories. For example, in 2014, Tiberi Wark was able to generalize, or at least give a thermodynamical interpretation of the non-conservation of the energy momentum tensor. In particular, this non-conservation is related to an irreversible flow from the gravitational sector to the matter sector, which could, in principle, produce matter from the gravitational fields, the so-called gravitationally induced particle production. But there are other works, of course, for instance, investigation of compact stars, investigation of inflationary scenarios, late-time cosmic solutions, and even traversable wormholes. Speaking of previous works, I take the opportunity to show some of the previous works that I fortunately took part. The first one is gravitationally induced matter creation in scalar tensor f of RT gravity. Basically, following the seminal paper of Tibério Arco, we basically explored such a phenomena in this theory. And these are basically the main conclusions, is that in our analysis, we concluded that, interestingly, the trace of the energy momentum tensor can be seen as a non-minimal geometry matter coupling by itself. And these two consequences, more to the cosmological side of the research, is that the universe can gradually build up entropy as particles are created. And we had some cosmological solutions in which we can have late-time cosmic acceleration without introducing dark energy, which is a very good result. The follow-up was basically constraining the parameters of our models using MCMC analysis with Pentium Plus and HZ datasets. And interestingly enough, one of our models, in particular the f of RT model 1, is observationally more supported than the lambda CDM model gravity, and basically these Akaike information criteria, specific criteria. Of course, this does not mean that our model is better than lambda CDM model, but at least the results say that, okay, it's not too bad either, and some investigation should be also carried out. The final one, the third one, was also gravitationally induced particle production, but this time in another theory of gravity. There are no more conclusions. These are the same conclusions of the first work. Now, I'm going to present two works that I've been currently developing in the last couple of months. One of them is the pursuit of regular black hole solutions, which are solutions that resemble usual black holes, but without having a singularity in all its domain. And 2 + 1 dimensional f of RT gravity. Why 2 + 1 dimensions? Well, because some people believe that work in 2 + 1 dimensions serves as a theoretical laboratory that can grasp some interesting aspects or fundamental aspects of both quantum and classical gravity. And of course, it's much more simple. And of course, since these kind of black holes are not vacuum solutions, we need some matter content to generate such a. And in this case, following some previous works, we assume that such a matter comes from the so-called nonlinear electrodynamics. So here's our theory. The action of our theory is given by this following expression, where this f of RT gravity is a well-behaved function of both Ricci scalar and the trace of the energy momentum tensor, and this LF is the Lagrangian of nonlinear electrodynamics. By varying this action with respect to the metric, we obtain the gravitational field equations, and varying with the gauge field, we obtain its corresponding equations. It's interestingly enough, as you can see, due to the inclusion of the derivative of the function f with respect to the trace, we can see an impact, a direct impact that the trace of the energy momentum tensor provokes on the structure of the gauge field equations. It's a very interesting result. Now, since every theoretical work has a bunch of assumptions, here they are. So first, we assume that the f of RT function is given by this expression. This part was also investigated in the literature, so we basically add this extra term, in which lambda is a cosmological constant that can be written in terms of the anti-de Sitter radius. Moreover, we assume that the metric is both static and circularly symmetric, and the electromagnetic tensor is basically given by this expression. So the resulting equations from these assumptions is the following. We have this expression for the metric coefficient function, and this expression that comes from the gauge field equations. And note that, again, the presence of the coupling constant here from the trace of the energy momentum tensor that can change the effective value, effective magnitude of the electric charge. So in order to have the Maxwell case, that is the expression, the usual expression for the electric field, being with its corresponding expression for the Lagrangian density, we have this modification right here. And since we have a lot of freedom in choosing specific forms for these quantities, we basically assume the generic, this generalized expression for the electric field that recovers Maxwell in the asymptotic limit, because as you have seen before, we have basically 2 equations and 3 unknowns. So in order to have a closed system of equations, we need to assume something, and this is the electric field. With such assumptions, the simplest case is this one, where we were able to recover the Maxwell Lagrangian and also the so-called charged BTZ solution and the so-called BTZ solution. So at least our results are consistent with the literature. Yay! Okay, so let us focus on particularly the GR case, in which lambda is equal to 0. Our equations are much more simple. Then, assuming the previous electric field, we conclude that the Lagrangian has this monstrous expression right here, as well as the metric coefficient function. And although we could recover some specific solutions on the literature using these solutions, there are some specific solutions for the Lagrangian that do not recover Maxwell. For example, the case where alpha and beta are equal to 2. Okay, so as you can see, we basically obtain all the solutions, but when R tends to infinity, it does not recover Maxwell. So, okay, it's not a good result, but for the sake of completeness, we basically trace the figure of such a metric coefficient, and we see that for any value of A and Q, we have one event horizon, which is a characteristic of the usual black holes. But however, unlike normal black holes, both the Ricci and the Kretschmann scalar do not diverge in any point of space-time. So we conclude that this solution is regular. Yay, now that's a good result. Okay, but how can we have a Lagrangian that has a Maxwell-like behavior? Basically, we have imposed an extra condition, this one, okay? We basically say that that this limit should be 0. And if this limit is 0, then we have this relation between alpha and beta. So we basically substitute this relation on our general solution, which gives us these following new expressions for both the Lagrangian and for the metric coefficients. And of course, for the electric field, in which we have substituted alpha for beta plus 1. Okay, and here they are, our solutions until now for the GR case, in which, again, we can recover from these solutions several particular cases that are on the literature, but there are also new ones that are all regular, and this is at least a very good result. Yeah. The second work is a construction of a Palatini formulation of a novel generalized non-minimal geometry method coupling theory. Basically, there is a question regarding the choice of the scalars in order to have a non-minimal coupling. After all, what is the correct choice? Is it the energy momentum tensor contracted with himself? Is it the trace of the energy momentum? What is the correct choice? Basically, in this collaboration, we are trying to generalize an action that fits these particular cases together. And how can we do this? Basically, in this kind of theories, the first derivative of the Lagrangian with respect to the metric appear in all field equations. So it is natural to assume that this quantity here is in fact a fundamental field of such an effective field theory. So basically, we have constructed the action just like this, and you may ask, but why are you inputting the second order derivative? Because basically we are trying to understand the mathematical structure of the theory. It's not for physical reasons. And these are the only results that we have right now, with emphasis to the corrections to the energy momentum tensor, which again depend on quantities that we can see in these kind of theories. Let me just say that our theory recovers both GR and f of RT gravity, which is a okay result for now. And finally, just a brief comment regarding this preprint. I don't know if anyone on the audience is familiarized with this paper, but they basically challenge, or at least they claim that these kind of theories are not relevant for cosmology. And in my opinion, at this moment, I disagree, because the arguments that they use is the following. Here's the thing. They basically impose the standard model of particle physics to scrutinize cosmological models and these kind of theories. And I think that since a modified theory of gravity is given by this generic form, so we have classical gravity plus classical matter. Of course, in these kind of theories, we can have a mixture of both, but nonetheless, it's always classical. One should ask the following question, that is, since every term in the action is classical, can we realistically include a quantum field theory that lives in Minkowski spacetime, which in this case is the standard model, in it and expect accurate predictions? So this is my genuine question. And of course, I may ask you if I am just sort of ignoring some aspects or anything, but yeah, that's basically it. In this slide, I summarize all the conclusions, so feel free to read them. And thank you very much for the opportunity to speak.
Thank you, Miguel, for your talk. Questions or comments? One question. Six in the front.
Thank you for your nice talk. So I'm wondering, because when you have nominal couplings, the definition of the stress energy tensor, I mean, it's always tricky. So I mean, I was wondering, because in these F of R T theories, I mean, it seems that the stress energy tensor you would define somehow doesn't a priori wouldn't coincide with the stress energy tensor you're including in the Lagrangian. So what's the actual definition you're using here for the stress energy tensor?
The definition of the stress energy tensor is the usual one. It's just like GR.
You mean the Hilbert one, the one partial of Lagrangian with respect to the metric?
Yeah.
So I mean, so if I have a question, if I have an F of RT theory, and I perform this partial derivative with respect to the metric, I will get the correct result for any function of the trace of the stress energy of the stress energy tensor.
I believe so. Yeah.
Okay.
Yeah.
Any other question? Comment? No? So let's thank Miguel again. Now, the last speaker of the morning, Thiago. Okay, so Thiago is going to speak about something. So I don't see the title. So surprise, be ready for everything. The pointer, maybe Miguel. Sorry.
Could you give me a warning if I miss?
This is just a part.
And then could you give me a warning of 5 minutes and then 2 minutes?
Yes. Oh, this is. No, yes, we have a title. It's hidden. Okay.
So yes, hello, good morning.
So I've given a grand title to this talk, but a more realistic one would be help. Hopefully you'll understand why I need some help. The outline of my talk is this one. So a great mess all over the place. And I want to start precisely here by asking you if anyone knows what this is. I give you a hint, it's nothing to do with physics, at least not directly. Anyone?
Is it related to music or something?
Yeah, actually, yes. It's, believe it or not, it's a musical script. We're used to seeing music like this, whereas this one is by Yannis Xenakis, who's an architect, but also music composer, and he completely reinvented his way of writing music like this. And the reason I'm bringing this up is that sometimes I think of modified gravity like this. So we're trying to do something different and see what comes out of it. In particular, the work I've been developing, it's more on getting the on the cosmological side and to do phenomenology to get late time expansion. So we're modifying gravity to get the universe accelerated expansion. In particular, in the last year, I've been working in FFQ gravity. So again, we've seen this. The gravity can be defined in these three different ways. The on top curvature, here torsion, there non-metricity. And then we can extend these models to do modified gravity. And I'm this past year I've been doing FFQ, so functions of the non-metricity scalar. Okay. The model I've been working on is this one. So it has a logarithmic term in this non-metricity scalar. And the interest of this model is that this logarithmic term can give us a self-accelerating branch. In other words, we can have the accelerated expansion without having to include any exotic dark energy field. Then what I did is to study the cosmological background evolution and the linear perturbations evolution, modifying a numerical code to compute the observables. So we have here, for instance, the cosmic microwave background power spectrum, TT power spectrum, in the middle, the lensing power spectrum, and in the right, the matter power spectrum. And then the idea is then to getting the observables for this model and compare to the standard model, say the Lambda CDM1, and then see what happens. There's some indication that maybe for some choice of parameters, maybe we could improve on the S8 tension, for instance. We got, maybe I'm, okay, we got a spoiler already on Monday with a brilliant talk by Alejandro, that recently there have been these works pointing out that these theories may be problematic and possibly not appropriate for cosmological studies. So we're in trouble now, because now we're not sure how to motivate our work if we want to submit it for publication. However, there's something more, because for years I've been hearing this, that, I mean, we love our standard model of particle physics, we love our standard model of cosmology, and yet they're incompatible, and we know they are incomplete. We need something more. And often I feel that what the work I'm doing we're trying to modify gravity. So in a way, in this musical sense, maybe we try to include some sharps there to try and modify a little bit and hopefully get some effect, in my case, to get the accelerated expansion. But in the end, it doesn't seem to solve much. It doesn't feel to me, all over these years, we're not getting anywhere. We are having more and more models, and we're not getting very far. So somehow I feel that we need more radical modifications to gravity, more creative, crazy ideas. To do that, I decided to do in this presentation also some to raise some questions, crazy questions about mass, because speaking about mass, I'm also speaking about gravity. And my idea here will be to do some curious observations about mass, going right away from the tiniest particle to the largest black hole. Now, your alarm bell should already be ringing. I'm talking about very different scales, so I'm bound to probably make some mistakes. But my idea is not to to say something correct or make correct questions, but really to do a brainstorming. So to create some discussion, perhaps. And to do brainstorming, we have to momentarily switch off our critical brains and let ideas roam free. And then eventually we do need to go back and switch on our critical brain to do some scrutinizing. And then I'm counting on you, on all of your expertises, to then do that, precisely that. So let's go that. Mass. If we start with E equals mc squared, or the more complete dispersion relation with the momentum and mass, we could say that in some way mass is the projection of the energy in the rest frame. Okay, mass, the projection of energy in the rest frame. Very well. Okay, so let's take a particular mass. What happens if we warm up this mass? The internal energy of this mass is greater. So does that mean that, so the projection of energy in the rest frame, so it's still in the rest frame, will that mean that the mass is greater as well? So warming something up will make it heavier. Now that's weird. Maybe a little bit less weird if we think that maybe to warm a mass, we could do it, for instance, by shining some light on it. And we know that in some way, radiation also gravitates. So all energy gravitates. So, well, that's it. Let's look, for instance, at the example of a black hole. Let's try to warm up a black hole by, again, shining some light on it. In principle, the black hole wouldn't care about what kind of particle is falling into it, right? So whether it's protons or photons. So if I'm shining light on it, sending photons into it, possibly the mass of the black hole will increase by the energy I'm putting into it. Now, here's an aside. If I'm trying to warm up the black hole, sending photons into it, and if the mass really increases, then if indeed the Hawking radiation temperature decreases with increasing mass, then are we trying to warm the black hole and then it's actually making it colder? But let's go back to everyday objects. Warming everyday objects, would that increase their mass? If it would be a very small difference. So raising the temperature by a few degrees, the difference in mass would be very, very tiny. So wouldn't make much difference for this. Maybe it would be more impactful on Andrea's planet and satellite, perhaps, because it's such a small planet. But it wouldn't be. It would be very small. How much how much do we need to raise the temperature to really get a significant amount in a significant increase in mass? Let's simplify it and think, for instance, on a let's say a gas of protons. And here I'm representing, this is my representation of a single proton with its quarks. So I have this gas of protons, and I want to warm it up in such a way that the increase in mass would double the mass of this gas of protons. So I want to double it, so I can really see what difference that makes. What temperature do I need to raise this gas to verify this doubling in mass? Possibly something like 10 to the 13 Kelvin. That's a lot. That's actually the temperature of the early universe when we have a plasma of quarks. So the temperature when there's a transition, the phase transition between the quarks and having the protons. So in a way, we're trying to warm our gas of protons, and by warming it so much, in a way, we made the quarks to evaporate, and this phase transition, so the quarks evaporated, and to this plasma. So a bit, I mean, even in the water, we could even warming 100 degrees would make the water eventually evaporate, for instance. Okay, so but another interesting thing about curious observation is that the mass of the quarks in the proton is only about 1% of the mass of a proton. So in a way, could we say that the mass of the proton is mostly binding energy? Okay, let's go back to our E dispersion relation. So we say, for instance, photons are massless, so they have only momentum. And other particles, we say they have mass and possibly momentum, but if we look at the rest frame, we only see the mass. So, okay, to go move faster. Okay, so what about if all particles are massless and the mass is only like an internal momentum, almost like a temperature? What if it's like they are composite particles? What does that have to do with, for instance, neutrino oscillations? Why do neutrinos oscillate between mass eigenstates when they are traveling within the sun? Let's go really crazy. If mass is if mass can be binding energy, what does mean, for instance, for the dynamics in galaxies or clusters of galaxies? Is mass more than the simple sum of the individual masses? What does this have to do with the gravitational and inertial mass, if we are talking about dynamics? I will skip this. So sometimes modifying gravity can be, at least to me, feel a bit of a mess. But can we go beyond it? And here I'm doing a play with the letters of GR and turn GR on its head and come up with some revolutionized gravities and really go, I'm going to also skip this, and really going to something out of the box or do away with the box altogether and come up with creative ideas. So this is this is the summary of my talk and the take-home message of my talk. Or if you prefer a more Valencian example and an architectural one as well, this out of the ordinary architectural example, which I also find very beautiful. And I thank you very much.
Thank you, Thiago, for your very original talk. So what if now we ask some questions? Anybody wants to comment anything? Come on. This is one of the most original talks of the meeting.
First of all, thank you for your talk, Tiago. It was very, very good. I think we have speak about this before. Remember that when you are talking about the mass of the proton and the mass of the individual quarks, remember that if you are trying to refer it as a binding or a sort of a binding energy, it should be more the opposite, because the binding energy actually removes certain mass from particles, for instance, in nucleus. Okay, the mass of a nucleus is the mass of the protons plus the mass of the neutrons minus a binding energy. So it should be a positive binding energy. It was, yeah,
yeah,
but
I mean,
yeah.
this is precisely what I want. I want feedback. I want to, and me, even not particularly on this, but really to get together and come up with crazy ideas.
And then again, these, I am not an expert on QCD, but the mass that the proton has have a lot of contribution that the self-interactions of the gluons. So in that sense, it has a sort of an internal dynamics around it. So it goes to your idea in a certain way. So
yeah. So actually, maybe I'll take that and go back to that thing I've skipped, because it's also interesting that if we combine the two grand equations of the 20th century, in some ways we have that to each mass there is an associated frequency. So yeah, there's a frequency. Is there frequencies? Does that mean dynamics? Does that mean, what does that mean? So I'm not sure if it's.
No, yeah. I think so. We can discuss it later.
Any other question? Yes,
just a comment. I also share the feeling that in modified gravity we are kind of lost. We wrote some essay with some irrelevant colleague for the gravity awards, and we didn't get too much attention. So the paper is still there in archive. But well, maybe it's not related with your topic, but there is some sense of beauty or simplicity in order to modify gravity. But this conception is really different for each person. Like some people will say, the simplest modification to gravity is this. The simplest is this. The simplest is supersymmetry. And then it's quite a lot personal things. So what we are lacking probably is experiments to guide us on how to modify. Unfortunately, we won't reach Planck scale until, who knows, 100 years, we don't know. I hope sooner with some revolution in artificial intelligence, I don't know, but yeah, I share your concerns. It's just a comment.
Thank you.
Any other comments? Yes.
So thanks very much for your nice talk. That my question is more than which kind of revolution do you expect? A classical revolution or a quantum revolution in gravity?
Good question. Well, I don't know, but so the usual thing is to say we need to quantize gravity. Roger Penrose, for instance, he says no, we shouldn't quantize gravity. We should geometrize, or we should geometrize quantum physics. Now there's recently it's been published a paper on post-quantum classical gravity. So they say that it could be possible to do a coherent theory where you have classical gravity, fundamentally classical gravity, and fundamentally quantum gravity, and they being compatible together. So who knows? But my hope would be to be something completely different, because I'll also take your thing and go to this thing that I missed, because on Saturday I went to a show on the Hemispheric in the City of Sciences and Arts, and in that show I was reminded that since ever we've known about electricity phenomenon. but even by the 1800s, we still knew nothing about explaining it or how it worked. So my hope or my gut feeling would be maybe it's probably something could be very different, because I mean we work with descriptions, so we can describe things different ways, and maybe sometimes it's more personal things. So who knows? What would you like to? What would be your point?
I don't know, but I hope also that it's something different that we don't understand. Instead, before he said that the geometry has an importance and the masses and the geometry interacts. Perhaps we are missing something that we don't know right now.
Okay, any other question or comment? So just one thing, following the lessons of Copernicus, we are not at the center of the universe, neither at the center of time. So maybe the revolution will come not in our lifetime, but in the future. So thanks a lot for your talk, and thanks to everybody for the morning session. Now it's time to stop and go for lunch. Let's thank Thiago again.
Aparte que creo que Hispanifica que ahora mismo en la crisis y probablemente va a ser en el campo